A very good afternoon to all. I am Annesha Shingupta and it is my pleasure to be a moderator for this session today. Today is the third day of our 5 days FDP program on applied mathematical skills for science and engineering using contemporary tools. We are organizing this FTP from our Applied Science Department of MAKAUT WB in collaboration with Islamic University of Science and Technology, Jammu Kashmir, sponsored by DAY-3. Today in this panel, we have Professor Dr. Shukhendra Shamazar, the Director of School of Natural and Applied Science, Professor Rathapallo Bhatt, HOD of Applied Science, and our distinguished speakers, Professor Molay Banerjee from IIT Kanpur, Professor Kushumdeep from IIT Roorkee, and Professor Vinay S. Chaudhary from IIEST Shibpur. My colleagues Dr. Abhay Vishwashwada and Dr. Shankar Prasad Mondal sir from Applied Science Department. I believe that our participants will enjoy the session fully, as the session covers such interesting topics like mathematical ecology, application of optimization theory, and also the quantum theory. These topics are really very important for uh, research activities, as well as for teaching purpose like and engineering and industry also. Without taking any more time, let us start our lecture session. Today, our first speaker is Professor Molay Banerjee from the Department of Mathematics and Statistics of IIT Kanpur. Professor Banerjee, an eminent professor and researcher in the field of mathematics in India. His area of research interests are mathematical ecology and ecoepidemiology, nonlinear dynamics. He has more than 156 publications in various reputed international journals. He is also an associate editor for two special issues on COVID-19 modeling for the journals Mathematical Modeling of Natural Phenomena and Letters in Biomathematics. We are very happy to have him among us today and welcome cordially Professor Banerjee to our UTP. Today his title of lecture is An Introduction to Mathematical Ecology. I request Professor Banerjee sir kindly deliver your speech. Sir, please.
Thank you. So let me first share my screen. Is it visible?
Yes, sir, it is visible.
Okay. So within this talk, thank you very much for kind introduction. And frankly speaking, I'm a little bit hesitant with all this introduction, but anyway, it is formality from your side. Thank you very much. And also thank you for inviting me to deliver this talk. I will try my level best to give you some ideas which might be interesting as well as encouraging, but I can't assure whether those are going to be thought-provoking or not. If towards the end it is thought-provoking, then my target will be fulfilled for the delivering of this lecture. In this lecture, I'll go through mainly 3 different points. First one is single species population growth. Second one is 2 species population growth. And then I'll come to spatiotemporal pattern formation part. For single species population growth, let me first show you a couple of pictures. These are examples of different species that we can see within our natural environment. This one is a picture for algae. There are different types of algae present here. This is a picture for fungi, and these are aquatic, nice looking fishes. Of course, this is not a real picture. Rather, I like this colorful picture very much. And then on the right, you can see different animals those can be found within a natural habitat of the forest. Now, once we are talking about single species population growth, then most of the time people are considering just growth equation, most of the people, without keeping in mind that which single species population they are going to model. One natural question might arise that is it possible if we look at the equation, then we can understand that, okay, this is an equation for algae, this is an equation for fungi, this is an equation for some aquatic animals, or maybe specifically for fish, and then this is for wild animals, etc., etc. Precise answer is no. Rather, this is a very sophisticated modeling approach. Most of the time, we can see just one or two models. But my main intention of this lecture is to give you some clear-cut idea that how, even in case of single species model, the modeling formulation plays an important role once we interested to incorporate some of the exposed features of the species under consideration into our modeling approach. First, single species population growth, it was introduced for some bacterial population, but the important progress, that means conversion from exponential growth model to logistic growth model, took place while Malthus look at the US population growth for a couple of years. I am not showing you the exact data which Malthus used for his population model, but I am showing you a different picture that is taken from a particular source, where you can see two different type of growth if you change the time window of your observation. Figure is this one. This is a growth curve for part of the US population which contributes to the foreign born population. What is the interesting part? Interesting part is, if you consider up to this level, so that means starting from 1960 to 2000, it seems to us that this population grows exponentially. But now, if you consider up to 2017, it shows some kind of saturation. Although it is a single species population growth, but if you try to understand that what are the main factors which changes the growth pattern from exponential to saturating growth, then you can find several factors. Some of them are socio-economic factors, some of the immigration policy factor, etc., etc. Different policies are there. And once we are interested to construct a mathematical model which follows certain strict postulates of mathematical logic, then most of the time it is quite difficult to capture the realistic variability that is observed within the nature. But with this much of information, first of all, I can show you the simplest single species population model That is exponential growth model. So what is the basic assumption? Basic assumption is that rate of change of population with respect to time, that is n, is proportional to the population density, and hence the rate of change is equal to Rn. This R, sometimes people call it as birth rate, but actually this is net growth rate. This R is the difference of birth rate and death rate. This is the simplest model. If you look at the saturation, then this saturation can be captured through the introduction of another term, that is this factor 1 minus n by k. With this introductory term or newly multiplied term, we can capture this saturating growth. So that means initially there is a positive growth and then it attains some level, assumed to be remains there for all future time, based upon the assumption that none of the background conditions are going to change further. But actually it keeps on about time, then the question of time scale will be coming into the picture. I am not going into that particular detail. Probably in that case, I need at least 10 lectures to deliver in a successive way to explain each and every point. So then what I'm going to do here, I'm just going to show you that instead of considering first equation, if I consider the second one, what will be the outcome? For the first one, that is dn dt equal to Rn, this shows some sort of exponential growth. But once you introduce this factor 1 minus n by k into the modeling approach, then certainly it changes to some sort of saturating behavior. Now, at which point it start declining or start exhibiting some sort of saturating behavior, what is the rate of growth? These different components gives us the appropriate measure for R and K. Although it was explained in Malthus model that this type of model sometimes fits with the human population, but as per my personal understanding, these type of equations are actually fitted well for microbial population growth, not for human population growth. And that factor is clearly depicted in this particular picture. And this picture means if you look at the different age or stage of the human population, then humans at any age cannot reproduce, cannot give birth of new offspring. So therefore, it is required to be divided into 3 groups, and hence age structure or stage structure model is most suitable to describe the human population growth. So this is just as an introductory slide, and to explain that how if we change from one model to other model and consider different time scale, then instead of having an exponential growth, it can changes to saturating growth phenomena. Now, once we're talking about modeling of ecosystem, then first of all, we need to understand which single species we are going to model. Any natural ecosystem can be divided into these kind of 5 groups. And I am not saying that every ecosystem can be divided into 5 groups, but this is more or less complete picture. Some ecosystem may have less number of compartment, or some of them have some sort of more subdivision of this particular compartment. But in general, it starts from primary producer, which are autotrophs, then primary consumer, herbivores, then carnivores and omnivores, and these species are coming into the picture one by one. Now, once we are going to consider a single species population model, then we need to keep in mind that among these different level, which level we are going to model. Just for example, are we interested to construct a model for primary producer, or we are going to construct a model for, say, carnivores or omnivores? Depending upon that, we need to choose appropriate functional form to describe the growth of the single species population. Now, for your quick understanding, again, I'm going to show you a couple of nice pictures such that you can understand that how and in which manner these trophic levels are distributed at different level. So these are the some pictures of autotrophs. Each of them are autotrophs, but this picture clearly indicate that if you look at very minute characteristics of the autotrophs, then they can be specified into different classifications. So once you are going to construct a model for, say, autotrophs, then you need to be very much clear from your basic assumption that whether you are constructing a model for a particular species or you are constructing a model for general autotrophs. So these are very much important. Secondly, if we look at the herbivores, these are different examples of herbivores. Why I have considered these many pictures here? Just to give you one quick understanding that this particular species giraffe, they are consuming some leaf from some big trees, but this antelope or deer or this rhino, they are looking for some grass or small autotrophs for having some sort of food for their uh, living beings. And then if we look at the carnivores, then these are different examples. And finally, if we consider omnivores, that means these species, they can survive on both, sometimes this autotroph and sometimes small herbivores, and maybe sometimes they are looking for some dead animals and etc. So the interaction between them is quite complicated. And the interesting point is that which single species you are going to model, that pose a very great challenge to choose the appropriate functional form to model the ecosystem. Now, in terms of this model, this is the well-known logistic growth, and I can give you some sort of open challenge that if you look at the wide literature on this mathematical ecology, then you can find around 80 to 90% manuscript, they dealt with this type of logistic growth. But ultimately, I'll show you that what is the main drawback of this model, and probably some new trend of research will come up in near future where we need to replace all the logistic growth equations by some other equation which are already started coming into the daily research slowly. So personally, I prefer this kind of parameterization of this equation, that is an minus bn square, only for the reason because this r, it should not interfere the growth rate of singleton population, or sorry, as well as intraspecific competition term, because this n squared term comes into the picture in order to model the intraspecific competition. So therefore, R is interfering both the linear term as well as non-linear term. This is not really acceptable. So it is better to consider this equation as an minus bn square. Now, equivalently, if we write this equation as n times fn, and then if you look at the plot of this fn, so fn is clearly your a minus bn, where a and b are both positive, then you can understand this is a straight line joining these 2 points. if you look at this picture, then you can understand that when population is approaching to 0, then growth rate is maximum. Believe me, this is a blunder. What happens if we are considering growth of any microbial population? Then it is possible, because at small population density they have enough amount of nutrient, and once the number of cell or microbial bodies increases, then there will be a decline in growth rate. But in case of two-sex population, it is impossible. Rather, you can find several examples where very small amount of population may be surviving, maybe facing some great challenge for their survival due to having a rare chance of successful mating. And therefore, for two-sex population model, what kind of growth curve we need? We need a growth curve either of this term. So that means at low concentration, it is positive and in a growing mode, or it can have at very low concentration, it is negative and then start increasing. So what kind of modification is required in order to capture this kind of growth rate? We need to introduce one factor, that is n plus alpha. And this is not a dedicated course on mathematical ecology, so I'm not going to explain in detail, but just for if you are curious, you can contact me personally. I can give you more details how this function can be derived. Actually, there are some mechanistic way out to derive this kind of functional form. And in this case, this alpha is positive. But if it happens that at low population density, there is a rare chance of successful mating, so that means there will be a negative growth rate at low population density. So then growth curve looks like this one, and then you need to change the growth equation a little bit. Just instead of n plus alpha, you can write n minus beta, and it explains clearly there is a restriction that beta should be less than kappa. Now you can ask me the question that in the previous slide you have said that r into 1 minus n by kappa is not a good choice, but still you are using here. I'm using here only from the reason because I have taken this equation from the paper of Berek and Ludwig afterwards, who wrote a book on Alley effect, and just to follow with their same notation, that's why I kept here. So there is no harm if you take this row inside this bracket and replace it by a minus bn. So in general, functional form is not going to change drastically, only there will be a change in parameterization. So irrespective of the parameterization, we can have this kind of functional form, and precisely I can give you a justification. This n square, it actually represents that what is the probability of successful mating between the productive male individuals to productive female individuals. So this n square plays a crucial role, and that is actually responsible for this kind of increasing growth at low population density. And again, this function gives us another nice feature, that initially it is increasing, then both of them reaches at some maximum and there is a decline. So what is the interpretation? Interpretation is that up to certain level, they cooperate among themselves for the growth of the population. But once they reach at certain threshold value, after that, there is some sort of intra-specific competition to have access to the available resources or having favorable habitat. And that's why competition comes into the picture, and that is responsible for decline in growth rate. And of course, nowadays, some group of people like Vitaly Volpart and Sergei Petrovsky, they have started working on the factor that how socio-economic factors can be incorporated into the modeling approach, such that in case of human beings, at least for human beings, this kind of decline in population level based upon economic situation of the market can be captured. Of course, there is a debate whether it is really a matter or not for remarkable change in the population density, but of course that is a new area of research. So this is another kind of growth equation. Now, what is alley effect? Alley effect is actually an effect which is responsible for increasing growth rate of the population at low population density. That can happen due to several reasons, as I have mentioned, that due to shortage of fertilization or mating encounter. So in case of autotrophs, this is a shortage of fertilization, and in case of animals, there is a shortage of successful mating encounter. There are some sort of other kind of behavior, like some sort of huge grazing pressure by their grazer or habitat destruction. Different possible mechanisms are responsible for lowering in the growth rate at low population density. This is just a list of a couple of such phenomena, but this is not the limited list. Rather, there is a complete list of 13 to 15 different mechanisms which are responsible for the alley effect. So what is alley effect? Precisely, I can mention that increasing growth rate at low population density, and then it reaches some maximum at an intermediate level and then start decaying. This kind of growth phenomena is called the growth affected by the alley effect. And it was introduced in the literature in 1927 by W.C. Alley, but nowadays it becomes popular during last 10 to 15 years. Prior to that, most of the literature deals with the logistic growth law, but this is more suitable choice for considering single species population growth. Now you might be wondering, those are the limited functional form for such kind of mechanism? Answer is no. These are other possible functional forms to model different kind of single species population growth. So as I told you earlier, that there are growth of different trophic levels. So depending upon that, you need to choose appropriate functional form. Most of the time, this particular form is suitable for autotroph growth equation. This is also true for some autotroph, but not for aquatic, that means plankton population. And this is mostly suitable for some bacterial and fungus population, and for two-sex population, either this one and some other forms which involve some cubic nonlinearity explicitly, those are most suitable for such kind of interaction, single species population growth. Now, analysis of single species population model is relatively easy, because most of the time the behavior of the system can be understood from the graphical analysis. So for this type of equation, what is the main burden? The main burden is that you cannot find out solutions of these equations explicitly. And that's why what we can do, we can try to find out some of the equilibrium points. What is the definition of equilibrium points? Equilibrium points is simply the rest point. That means the points at which the velocity, that means growth of the population with respect to time, is 0. So that means if you solve this equation algebraically, that means this expression is equal to 0, then clearly you can find three different values. One is n equal to 0, another is n equal to beta, and another one is n equal to kappa. And graphically, you can judge their stability, because this function, if you plot in n-Fn plane, it looks like this one. So this is your equilibrium 0, this is your equilibrium beta, and this is your equilibrium point kappa. And from the position of this point, you can understand this is 0, this is kappa, and beta lies between 0 and kappa. And this function is positive within this range, and it is negative within this range. So this means that n is increasing over this interval and n is decreasing over this interval. So if you choose some initial point here, then population will increase and ultimately converge to this point. So therefore, this is a stable equilibrium. And if you start from some point here, then it will start moving away from the point n equal to beta and ultimately converge to the point n equal to 0. So therefore, this one and this one is stable and this one is unstable. So what is the ecological interpretation of the result? Ecological interpretation is this: if your initial population density, that means n0, if less than this particular threshold, then it is expected that population will die out because they will become extinct. This deterministic model predicts that. And if it is greater than this particular threshold, therefore it will keep on increasing if no other mechanisms are involved into the modeling approach, and ultimately it will converge to this particular value, that is n equal to kappa. So this kind of mechanism is called bistability in the system, and this is your unstable equilibrium. These two are stable equilibrium point. Now with this much of information, now we can proceed to the discussion about the two species population growth. In case of two species population growth, this is a famous data set available over 100 years, but that was collected only for two species, that is only hare and lynx. So what you can observe here, that for single species population growth with deterministic setup, that means without stochasticity and without explicit time dependent parameter, all the times you can have uniform convergence towards some equilibrium point. But in order to capture this kind of varying population density, so Rosenwick and MacArthur, they construct a prey-predator model with saturating functional response in order to fit the simulation result or outcome of the model with this kind of variable data set. And they approximated this data with a periodic solution, and which actually realistic for these two population observed over several decades. And that's why they tried to construct a model and estimate some of the parameters in order to have this, or in order to capture this kind of oscillatory behavior of two populations. What is the Rosenwick-MacArthur model? Rosenwick-MacArthur model is given by this one. So now you just try to understand this part, that means n into alpha minus beta n. This was the single species population growth, and this is considered as prey population. That prey population is consumed by predator. So this particular functional form describes that at which rate prey individuals are killed by the predator or consumed by the predator, and then once the predator survive on this prey population, a fraction of this consumed biomass contributes to the growth of the predator, and this is the intrinsic death rate for the predator population. If you have a close look at this equation, then you can understand that in terms of predator population, this is an exponential growth equation, because you can take P common. So you have one function which is actually a function of time implicitly, function of prey population n explicitly. But if I call EAN by 1 plus AHN minus M as a single quantity, say G, then your equation is dP dt equal to GP. And this is the beauty of nonlinear equation. So once it is an exponential equation, but there is an positive feedback from another population, and this population can be proved to be bounded. So therefore, it never allows any exponential growth for the predator population. Rather, you can prove the solution of this equation once started from any positive initial condition, those remain bounded, and you can find out the invariant set within which solution will remain at all future time. Now, what are the interpretation of different parameters? Interpretation of different parameters are given here. I am not going to read this particular list, but you can just go through it quickly. Only one point I'd like to mention here, that this functional response, that is a n by 1 plus ahn, this is crucial because this function is actually connects the dynamics of two species. What I'm trying to say here, that this part is free from p, this part is free from n, but this is the term which involves both n and p. So therefore, a variation in n will be reflected on p and vice versa, depending upon these two terms. So therefore, choice of this functional response is very much important in order to capture the appropriate dynamical behavior. Now, you might be worried that how this kind of functional response is assumed. Most of the time people can say, okay, this is a well-known thing, you can do it, but I'll try to give you a clear-cut justification that how this particular functional response can be derived. So it can be derived in this way. For this purpose, we consider a few new variables. So n is the number of potential prey, that means which can be accessed by the predators. V is the number of prey caught. So that means how many prey are killed by the predators. So that means it is can be considered as victims. Then T is the total time window over which we are looking for. And TH is the handling time for each prey item by predator or a group of predators. I am not going to distinguish between these two cases, but believe me, depending upon this distinction, whether a prey individual is killed by a single predator or a group of predator, depending upon that, your functional form will change. But just for an introductory part, I'm not going to distinguish between such phenomena, but rather we can just consider this is a handling time by per prey item, maybe by a predator or maybe by a group of predator. But what is the assumption for derivation of this functional response? Assumption is that number of victims is proportional to the number of potential prey, and number of victims is also proportional to the searching time. So that means if number of potential prey increases, there will be increase in number of victims, and if there is a longer window we can find for the searching time, then again number of victims will increase. But keep in mind that this is not the characteristic feature for all the predator items. Sometimes there are certain examples of species of predators which kills prey but they never consume, and sometimes you can find examples of such kind of predator population. They are going to search and kill prey only if they are hungry. So depending upon the particular species, you need to choose appropriate functional form. Now, based upon this, what we can write? So first of all, victims is proportional to the number of potential prey, well understood. That is V proportional to N. But how to derive this condition? That victims number is proportional to the searching time. So T is the total time. TH is the handling time for each prey. Therefore, total time they spend for handling V number of victims is actually TH into V. So therefore, searching time is nothing but T minus TH into V. This is your searching time. And therefore, you can find that V equal to alpha times this. Here, alpha is the constant of joint variation. And from here, if you solve for capital V, then you can find V equal to this one. And then V is the total number of victims over a time interval of length T. So therefore, per unit of time, number of victims is this expression divided by capital T, which gives you phi n is equal to this one. And here A is called the rate of consumption, or you can say this is a searching rate or killing rate, and H is the handling time. This H is actually replaces this TH here for the simplification, and therefore this functional response is now probably justified to all of you to understand from where we can find out this kind of functional form. Now, as I told you earlier, there are different kind of species, and as a result, we need to consider different types of functional form to model the functional responses. And here is a list of such kind of function. Again, it is not the exhaustive list. There are few more functional form which are responsible or which is required to model different kind of interaction. But first three functional response, they possesses same kind of characteristics, although their mathematical form in terms of the variable n is different. This one is holding type 3 functional response. It can be easily derived from the previous one, because if you assume that this alpha in the previous equation, that means in holding type 2 function response A, that means the rate of killing is proportional to prey population density. So that means if you replace this A by alpha n, so immediately from there you can derive this holding type 3 functional response. There are some non-monotonic functional response. It means it is increasing at low population density, then it attains its maximum and then start decaying, and therefore it is called non-monotonic functional response. This non-monotonic functional response is most of the time used in case of plankton ecosystem, where there you can find some sort of toxic phytoplankton which actually discharge some toxic substances within the environment, and therefore zooplankton and other grazers of those phytoplankton cannot capture them due to some sort of bad smell or different chemical composition within the aquatic environment. So therefore, although there is an increase in phytoplankton population density, but the grazing rate is not increased, and such kind of phenomena can be modeled by this function. There is another situation where this kind of formulation is true if a particular prey species exhibit some sort of hard behavior. Hard behavior means there are example of different animals which are caught by the predator if they are a single, that means lone within the natural environment. But if they are present in a group, so therefore it is very difficult for the predator to catch a single prey, and that particular phenomena individual increases, so there will be lowering in the grazing rate, and therefore this kind of functional form is suitable for such kind of interaction. Now, for this type of model, what is the standard analysis? Standard analysis is that already Professor Somoresh Pal discussed yesterday. So I am not going into the details of those linear stability analysis and classification of the equilibrium points and etc. But for your quick reference of this model, you can find out three different equilibrium points. One is the trivial equilibrium point, that means there is neither prey nor predator. Second one is predator-free equilibrium, and third one is coexistence equilibrium. And these equilibrium points can be obtained by solving these two equations, fxy equal to 0 and gxy equal to 0. And this equation is derived from the previous equations by rescaling of the variable in order to reduce the number of parameters. If you are interested to work on the dimensionless version, so therefore whether we are writing here in the original model is Rn into 1 minus n by k or n into a minus bn, that is not immaterial. But if you are very much particular about the ecological aspect or interpretation of the model outcome in terms of realistic ecological aspects, then you need to be very much careful about those parameterization. So in terms of dimensionless model, you have only three positive parameters, alpha, beta, and delta. And therefore, you can find that three equilibriums, and this coexistence equilibrium point is feasible whenever these parametric restrictions are satisfied. So that means the equilibrium population level of prey is moderate, it lies between 0 and 1, and alpha is greater than beta delta. It interprets that if grazing rate is greater than some threshold, only when only in that case coexistence equilibrium point exists. If alpha less than beta delta, so that means predator are not having enough resource for their survival, or they are not eating well for their survival, then they will go to the extinction. And if you look at the dynamics of this system, then four different kind of dynamics you can find out. This is the standard structure of performance of the linear stability analysis. Just for your quick reference, you can give a small perturbation around the equilibrium level to find out this system of linearized equation, where Aij are just the first order partial derivatives of f and g with respect to x and y evaluated at the point x star y star. And then the stability condition of the zero solution implies the stability condition of the concerned equilibrium point for original nonlinear system, and this is valid if and only if none of the eigenvalue of the linearized matrix is zero, or they don't have zero real part. This is called Hartmann-Grobman theorem. If Hartmann-Grobman theorem holds, that means linearized matrix have not a single eigenvalue which is zero or having zero real part, then the dynamic behavior obtained from linearized analysis is valid for the original nonlinear model within the small vicinity of the equilibrium point, but not far away from there. And for two-dimensional system, if these two conditions are satisfied, then we can say the zero solution, which in turn imply the concerned equilibrium for the nonlinear system is locally asymptotically stable, and loss of monotonicity property can be obtained from this restriction. That means when this is equal to zero. So what I'm trying to say here, that if you have two eigenvalues for 2 cross 2 matrix with negative real parts, then there will be two different cases. Either both the eigenvalues are negative real number, or both the eigenvalues are negative, having negative real part with complex conjugate eigenvalues. Now the threshold of a parameter at which eigenvalues changes from two negative real number to two complex conjugate eigenvalue with negative real part, that point is actually called the threshold of loss of monotonicity property. And this can be derived, that threshold, by solving the equation trace A whole square is equal to 4 of determinant A. And we can find an instability due to occurrence of Hopf bifurcation that is determined by these three conditions. So determinant remains positive, trace should be equal to 0, and you can check if trace is equal to 0 and determinant is positive, so these two eigenvalues are purely imaginary, and that is the Hopf bifurcation threshold. And this is called the transversality condition. Transversality condition means that real part of the eigenvalue changes its sign from positive to negative. If this condition is violated, then it means that eigenvalue is 0. That means real part of the eigenvalue is 0 at that point, but it cannot ensure that real part of the eigenvalue crosses the 0 line. It may happen that it is positive on both the sides or negative on both the sides, but touching the axis at the particular threshold. So in order to ensure the transversal intersection, this condition is required. So these are four different phase portraits. First one corresponds to the fact that predator free equilibrium is globally asymptotically stable. Then you have stable coexistence equilibrium. All the trajectory will converge to this point. This corresponds to instability of coexistence equilibrium surrounded by a stable limit cycle. And then finally, the size of the limit cycle keep on increasing with the increased magnitude of the parameter, and you have a large stable limit cycle. But in this case, what happens that once the trajectory moves through this particular portion, either this portion or this portion, there is a chance that either of the population can go to extinct, because they are maintaining low population density for a longer time period. So therefore, mathematical correctness gives you this kind of closed orbit, but this might indicate some possibility of extinction of the population. And therefore, if you look at the trajectory, you can see that prey population stays at this low level for certain time period, as well as predator population, they also remains at this low level for certain time period. So if this particular threshold is less than the adequate number of individuals required for their survival, so this may leads to extinction. So from mathematical correctness, we can capture that, okay, this periodic behavior is returning back, but ultimately it may have some sort of extinction scenario. Now, the general formulation of two-dimensional prey predator model looks like this one. That is dNdt equal to nfn minus gnp into p. So previous example I have considered with functional response, which is a function of prey density only. But there are examples of several population where you can find this functional response is not only function of prey, rather it is a function of predator population also. So therefore, GNP is the functional response, Fn is the per capita growth rate of prey, and QP is the per capita death rate of the predator, and this is the growth of predator due to predation. And these kind of models are called prey predator model with generalist predator, because if we assume QP greater than 0, so then predator population don't have any positive growth if N is absent. And it is standard practice to construct a function GNP in such a way that GNP is equal to 0 when N equal to 0. So that means if N is absent, then there will be a decline in predator population and they will become extinct. And therefore, for this reason, that predator cannot survive with this prey only. So therefore, this is called prey predator model, but with specialist predator. And in nature, there are very few occasions where you can find specialist predator. Most of the time, we can find generalist predator. I'll come to that point, that how an equation for generalist predator can be derived. Now, this is Holing type 2 functional response as I have described earlier. And from here, you can derive the ratio dependent functional response, which involves predator density also, where this N will be replaced by ratio of N by P. So when predator individual need to compete among themselves at low concentration of prey, so there then it can be proved that the functional response is not a simple function of N only. Then you can find this type of functional form which involves both N and P, and therefore you can find this type of ratio dependent functional response instead of Holing type 2 functional response. Now, once we are considering two species prey predator model, then you need to understand which two components you are considering. That means either autotroph and herbivore, or herbivore and carnivore for your modeling approach. And at the same time, you need to choose appropriate modeling formulations to capture the exposed dynamics. And this is a very simple example where you can see that combination of alley effect as well as this ratio dependent functional form. So with this equation, if you perform the complete analysis, I am not going to show you any mathematical details, but if you are interested, you can look at our paper on this particular topic. And for your information, all the papers are available in ResearchGate. You can easily download them. So if you simplify this model in terms of non-dimensionalized parameter, it will comes out to be in this particular simplified form. And finally, if you construct the complete bifurcation diagram, then in alpha 1 parameter space, the bifurcation curves divides the entire domain into 5 different regions. This blue line corresponds to transcritical bifurcation threshold. This magenta color curve corresponds to saddle node bifurcation threshold. This black color curve corresponds to the global bifurcation curve, that is homoclinic bifurcation curve, and green curve corresponds to the Hop bifurcation curve. And depending upon the choice of the parameter value from these 5 regions, you will have 5 different kind of dynamics. In this case, you cannot find any equilibrium point. In this region, you will find a limit cycle. Then here, limit cycle disappears through a global bifurcation. Here, only prey population survives, and this corresponds to complete extinction scenario. And the dynamics at different region looks like this one. This corresponds to complete extinction. In domain 2, you can have complete extinction, but some complex geometric structure arrives here. So what happens that if you start from this point, then both the population will be going to extinct, but it will take much longer time compared to if you start from this kind of low prey and predator population densities. And in this case, there is a small initial population density from which if you start, then this equilibrium point is unstable, but trajectory will exhibit this kind of oscillatory behavior. This black curve corresponds to a limit cycle, and this equilibrium is unstable but surrounded by a stable limit cycle like this. And then if you have in the parametric domain R3, then your coexistence equilibrium point is stable. And in R4, you have 2 different coexistence scenario. Either prey population will survive at their carrying capacity, or they will also go to extinction. But in both the situation, predator population always goes to extinction. So these are 5 different scenarios that you can have for this particular model, and which is a modification compared to the Rosenwig-McArthur model. But here the picture I have shown you, that is only for strong alley effect, but this model shows much more complex dynamics if you consider weak alley effect. But I am not going to present it here because towards the end I want to talk about little bit about the pattern formation. So just one more topic I want to talk about quickly. So this is well-known Lotka-Volterra competition model. Most of the time people are happy with this model as this is a model for Lotka-Volterra competition model. But from the beginning I was talking about that it may happen that you are considering a single species population, but that consists with more than one species. If the species are of identical nature, for example, they are sharing same habitat, they are surviving of the same resource, then what will happen, both the species belongs to the same trophic level, but they need to compete among themselves. And what is the new research goal nowadays? The challenging part is that can we combine several different species equation into a single equation such that the single equation will model the targeted trophic level. So what I'm going to show you that from this equation, you can easily derive the single species population growth under certain assumption. So here R1, R2 are their growth rate, A11, A22 are intraspecific competition for 2 species, and A12 and 21, these are interspecific competition term. But if you assume that they are identical, then what you need to do, you need to consider this equal parameterization, that is R1 equal to R2 equal to alpha, all Aij is equal to beta. If you substitute this, then you can have this equation, and now if you add these 2 equations, you can find this as the final equation, and then you can clearly understand instead of n1 plus n2, if you substitute simply n, then you can derive the single species population growth. Following this approach, we can derive an equation for prey predator model with generalist predator. How that can be done? That can be done in this way. Generalist predator means here predator has more than one food source, that is N1 and N2. Most of the literature have considered so far, majority of them, they have constructed this type of model. But I am not comfortable with this kind of model, because if you want to consider these 2 compartments, that means N1 and N2 as a single trophic level, then from this equation, you cannot write down the equation for dn dt and dp dt where n equal to n1 plus n2. And this is important because if predator survive on the similar kind of prey population, but there are some taxonomic difference between two species, so then you need to modify this model as follows, like this. So you need to incorporate this interspecific competition term here, and the saturation term also involve this n2 in the first equation and n1 in the second equation. So based upon this model, now if you consider that n1 plus n2 equal to n with some additional assumption on the parameters, you can derive the prey predator model with generalist predator. But interestingly, one nice idea is that if you consider that one population is available in abundance, so that means they maintain a constant value. So from here, if you substitute n1 equal to constant, so this term will be equal to 0. This will become an algebraic equation, and ultimately this model will become an differential algebraic equation, which is a very interesting topic for population dynamics nowadays. I am not going to talk about that theory because it is more involved. Just for your information, I like to mention that either combining these two prey population, you can have a prey predator model with generalist predator. And if you want to model the situation in a different way, that one prey population is explicit and another one is implicit. So what you can do, you can choose n1 equal to constant and rearrange your equation with the help of theory of differential algebraic equation to construct the prey predator model with generalist predator. Now we come to the topic of spatiotemporal pattern formation. I think I have 10 to 12 minutes more. Quickly, I can go through this topic. So what happens in case of spatiotemporal pattern formation, because we can find several types of distribution of different species over space, which are not in appropriate equilibrium state. Rather, there is some sort of heterogeneity. And in order to capture the stationary or non-stationary heterogeneous distribution of the population, although they are surviving in a coexisting fashion, so that's why these spatiotemporal models are very much important. So what are the different patterns? This is some sort of arid vegetation pattern. So in between you can find some sort of land or soil, and there are some patches where you can find some sort of autotrophs here and there. There are some other examples like ribbon forest. You can find this type of linear distribution of the trees in the ribbon forest, which are labeled as or termed as labyrinthine pattern. And what happens that due to human intervention, so maybe construction of some high road or maybe some sort of pedestrian road that is naturally created by the daily movement of some human beings. So structure of this array is getting altered day by day, not only by the human behavior, sometimes due to some sort of environmental condition, but it leads to some sort of distribution which is not homogeneous, rather heterogeneous. This is another kind of example that you can find two different types of trees. One are large and others are very small compared to them. And if you look at the geometry very carefully under idealistic environmental condition, so then it can be derived that this large tree always maintain a fixed distance between these two. And this kind of organization is called the self-organization. And if you incorporate some, if you just plant some new trees here in between, you can check, and it is already evident in the literature, that they will not survive. And that is called minimum patch size required for their survival. And that is due to for the distribution of their roots within the soil, and that creates a very crucial role for their distribution within a maintaining a particular distance among themselves. These are other examples of wetland vegetation. This is an example of some equidistant red cap terrace within the coastal area. If you look at their habitat, So they lives within the small holes, and if you measure, then you can find they maintain a appropriate distance, and those distance if are this means these nodes are connected by different line segment. So this looks like some kind of honeycomb, and actually these kind of spots can be considered as some hot spot or cold spot depending upon the species. There are another kind of situations that yellow whale, they are chasing a group of bluefin tuna, a small bluefin tunas, and what happens that you can find a interesting type of coexistence. So here you have a large predator, these are small prey. So the areas you can find where prey density is high, predator density is low, and vice versa. But keep in mind that this structure is not a static one, but it is changing continuously, and that's why these kind of patterns are called dynamic patterns. And the patterns of different species, that means for autotroph and then group living animals like elephant, and once the penguin, they are in a resting phase for certain time, not for a longer period. So their distribution can be classified into these three groups, that is either random distribution or clump distribution or uniform distribution. And then the question of change of this distribution with respect to time comes into the picture. Then patterns can be divided into two groups, that is stationary pattern and dynamic pattern. If they keep on changing, so then these are dynamic pattern. If not, then they are stationary pattern. And this is a nice example. That means if you are interested, you can have a look at this paper by Luca Ridolfi, who have shown that that is they able to make a tally between natural ecosystem, that is the vegetation distribution, and the mathematically obtained patterns which are matching with the picture in a nice fashion. And what they have done, they have introduced some sort of spatiotemporal reaction diffusion equation model with some noise term, and it is not possible for me to explain such kind of mechanism here, but rather I'll just consider only the partial differential equation part. So these type of patterns can be captured by this type of non-homogeneous parabolic PDE. So the reaction kinetics is now clubbed with the diffusion term and subjected to this type of feasible boundary conditions. So what we are assuming, that we are assuming the domain is finite and there is no inflow or outflow of species across the boundary. So therefore this is called no flux boundary condition and subjected to positive initial condition. And with this positive initial condition, if you choose your domain is a squared domain, then we can find out certain mathematical result for this type of model. So the result which leads to onset of spatiotemporal model, that is called Turing instability result. The idea is that you are looking for a homogeneous steady state which is stable under homogeneous perturbation but unstable under heterogeneous perturbation. What are the homogeneous steady states? If you are able to find out some solution of these two equations, that is reaction kinetics part, if you solve for equilibrium point, then n equal to n star and p equal to p star, these are the solutions of these two coupled non-homogeneous parabolic PD, because n star and p star, they are constant with respect to time and space. So therefore del n del t 0, this Laplacian of n is equal to 0, and f1 is also 0 at n star p star. So therefore these two equations are satisfied, and these kind of states are called homogeneous steady states. And now if you give a small amount of heterogeneous perturbation, that is p1 and n1, where this should be n1 and p1, not uv. Their magnitude is very small, and if you linearize, then you have this type of linear partial differential equations. And if you choose n1 p1 in this particular format, That means this kind of perturbation variable is introduced for N1 and P1, then you can find this type of characteristic equation. And this assumption for this answer of N1 and P1 is guided by the boundary condition, because if you differentiate these functions either with respect to x or with respect to y, you will get sine kxx or sine kyy, and which is 0 at x equal to 0 as well as y equal to 0, and you can choose your suitable wave number kx and ky in such a way such that sine kxl will be equal to 0 and sine kyl will be equal to 0 in order to determine the appropriate length of the domain which is required to choose in order to fit the unstable wavelengths. And just for stability criteria of this equation, if you derive the condition, then stability is given by this one. So that means the previous things trace negative, date positive. But interesting part is that for instability, what we can have, we can only violate this inequality, because for local stability we need A11 plus A22 equal to 0. D is a positive quantity, K is a real number. So whenever A11 plus A22 less than 0, then this should be always less than 0. So this cannot be violated. But what inequality can be violated? That means this one. So therefore instability can sets in due to violation of this inequality. And once this inequality is reversed, that is called Turing instability. And the explicit condition for Turing instability is given by this set of conditions. But interesting fact is that what we need, that we need simultaneously these two conditions are required to be satisfied. That means they are sum is negative, but once A11 is multiplied with a positive quantity, it will become greater than 0. So this indicates A11 and A22 should be of opposite sign for the satisfaction of Turing instability condition. And therefore, if you look at the Jacobian matrix, then Jacobian matrix corresponds to this format, gives you the appropriate structure or indication that whether Turing instability can exist for this system or not. So from here you can derive A11 and A22 product less than 0, and from this condition you can derive this is should be less than 0, and therefore Jacobian matrix's sign should follow any one of these four structure, and it will indicate whether a considered model for a chosen parameter value is going to exhibit or going to satisfy Turing instability condition or not. Just I'm showing you some pattern for this model. So this is just the extension of the earlier model that I have shown you. So here what we have introduced some intraspecific competition term among the predator. And interesting part is that if you just incorporate one such additional term, so for the temporal model, the bifurcation diagram changes drastically. And instead of having 5 different regions, here you can find 8 different regions. And I'm not going to show you the face portrait because time is limited, but rather I choose some parameter values and I can show you that a single model with different parameter setup can exhibit a wide range of spatial patterns. So this is the spatiotemporal bifurcation diagram. This blue curve is the Turing bifurcation curve. Green straight line is the Hopf bifurcation threshold, and red straight line is the global bifurcation threshold, that is homoclinic bifurcation threshold. So temporal model suggests that if alpha is greater than this particular threshold, so that if your value of alpha is greater than this, still population can survive, and that is the explanation for the real observation that okay, in that case instead of temporal model, spatiotemporal model will be most suitable one, and other parameter values are fixed at this level. And now if we choose different parameter values within this particular domain, we can have different types of patterns. So this blue circle corresponds to stationary spot pattern, black square corresponds to composition of spot and stripe, this green diamond indicates for this parameter value you will have labyrinthine pattern, and here that is magenta star corresponds to the domain where you can find some dynamic pattern, but actual nature cannot be speculated because system is quite complex and different type of dynamic pattern can result in. So this is the spot pattern. So you can think about this might be suitable for wetland vegetation pattern. Then this one is the mixture of spot and stripe that is obtained for another value, and on the right hand side it shows the transient behavior. So that means before come to the stationary state what kind of fluctuation they can exhibit, and then if you change the parameter value then you have this kind of labyrinthine pattern. So this structure might be suitable for ribbon forest case, and then if you choose some values for which D is less than 10 or maybe very close to 1, so then you can have this kind of spatiotemporal chaotic dynamics. And what happens here, this keep on changing all the time because the spatial average never converges to some steady state value. Although it shows some sort of periodic behavior, but some sort of inherent randomness kind of thing can be captured with these kind of PD models if you choose this kind of parameter setup. So therefore, I have taken just a snapshot of the spatiotemporal pattern at a particular time point, but this distribution keeps on changing continuously. So therefore, you can think about this is somehow distribution of the aquatic fish population, which are changing their position all the time. And as a result, within a particular domain, if you monitor their number, so they are continuously changing abruptly. And of course, appropriate functional choice and parameterization is required for understanding what is going on into the ecosystem. The most of the time I faced one question that, okay, you talked about one particular model which shows a wide variety of dynamics. Is it possible to find out one ecosystem which shows such kind of variable dynamics? Answer is no. Rather, what we are doing here, we are just forming a library. So if your reaction kinetics and mechanism follows this functional form and other formulation of the model, then what will be the expected dynamics for different choice of parameter values? So for one interacting species, your alpha might be 0.2, for another species it might be 1.3, and for another it is 2.15. So if you can tell me that for your model that these are the parameter values, so our analysis give you some sort of prescription that, okay, you can expect this kind of dynamics. And then the next question is that if it fails, it can fails because these are minimal model. So we can think about some sort of modification into the model formulation. So instead of this one, we need to consider time parameter explicitly within the model, or some sort of environmental fluctuation. Maybe we need to consider some other species explicitly which plays a crucial role which was overlooked at the initial position. So such kind of modification is required in order to understand or in order to capture the complete realistic picture. So I must stop here. These are some standard references for temporal model as well as spatiotemporal model. And I'm not showing you any one of my work here, but if you are interested, you can look at my Google Scholar list, or that is a ResearchGate account for having details of my work, and feel free to contact me for any further clarification. And I must acknowledge my collaborators from different parts of the world who helped me a lot for better understanding of different mechanism. But I just like to mention that whatever part of my work I have presented here today, that is done with mainly Andrew Morozov, Moitri Shen, Sergei Petrovsky, and Vitaly Volpart and Shahid Abbas. And some of our other works is done with some other people. And thank you very much for your attention.
Thank you so much, sir, for considering us from your busy schedule and also for that magnificent speech. In your lecture, you mainly describe a wide variety of mathematical models and analyze to understand the complex nature of interactions between several species within natural ecosystem. Though there are many more models like partial differential equation models, numerical simulation models, and ODA models. But ODA models are mainly used to describe the interaction between the populations. And also, you briefly explain the single species population growth and also two species population growth and spatiotemporal patterns. So, thank you for your kind speech. And now we shall take some questions from our participants. And for this, I request Dr. Shankar Prasad Manu sir, please take up the question and answer session. Sir, please.
Thank you, Molai Banerjee sir, for your nice presentation. So we have some question from the participant end. So the first question is, what is the significance of bifurcation in real life situation?
Okay, this is a very good question. Sometimes you can see in case of fishery that over exploitation of the natural resources can drive the system towards the extinction. So what will happen if this phenomena is true, or if you want to capture this phenomena, what you need to show that coexistence equilibrium point becomes unstable and one species is going to extinction. So therefore, if we move from the situation X star, Y star, it gets destabilized and some axial equilibrium of the point alpha comma 0 is now become stable. So that means second population goes to extinction, and this can take place due to over exploitation of the resources. Sometimes it can happen in case of some sort of pest control model. There are possibility to introduce some sort of biological enemies, and that is called biological control mechanism. Sometimes it may happen that one particular pest is damaging one crop. So what you can do, you can introduce a predator of that particular pest, and what will happen, that pest population will be going to extinction just due to the presence of predator for them. And that is another kind of bifurcation, that instead of having coexistence of pest and the particular crop, you are surviving only with the crop and another predator population, but that is not making any damage to the crop. Or it sometimes happen that due to some sort of change in environmental condition, some stable situation is broken down, and you can see some sort of oscillation in population density, which is mostly observed in aquatic system for plankton population, that is known as plankton bloom. So if you have a stabilized situation and all of a sudden you can see high rate of growth are followed by successive decay in the system dynamics, that is called the onset of some Hopf bifurcation, or maybe due to relaxation oscillation. So these are some mathematical interpretation of bifurcation which is observed in natural ecosystem.
Thank you, sir. Sir, our next question is,
tell me.
hello.
Hello.
Is modified logic
Hello.
am I audible?
And now you're audible. Okay, I can read the question. Is modified logistic growth model is same as 2D prey-predator model? I have already explained that logistic growth model is mainly true for single species. But what I have shown you, that from two competition equation we can derive a logistic growth. So it is same for 2D prey-predator model also. Next, there is one question, sir. Can we use same model in virology, or we have to? No, for virus dynamics, you need to consider some other kind of formulation. And if you want, you can have a look at the book by Kinard and Snide for mathematical physiology, where they talked about some kind of virus population dynamics, and even the book by Anderson, where some virus population dynamics model can be obtained.
Sir, I have a question.
Yeah, sure.
Is alley effect can incorporate with discrete system modeling?
Yes. There are several literatures.
That's it. And another question is, sir, is differential difference equation model can be possible in mathematical biology? Differential difference.
It is there. It is there, and those are actually called hybrid model. If the participant is interested, he can look at the some work by R.M. Nisbet, and the paper is available in Journal of Theoretical Biology, and they have shown in case of some insect population, at some stage their growth follows their growth is modeled by differential equation, but rest of the period of the time it is actually modeled by difference equation. So those are called hybrid differential equation. And if you are interested, there is a particular journal that is nonlinear analysis hybrid system. In that journal, you can find a couple of interesting papers on this particular topic, which deals with differential difference equation.
Thank you, sir. Another question comes from our participant end, that please, sir, tell me one book for real ecosystem that refer different kind of model.
One book for real ecosystem that refer different kind of model. In my slide, probably you have checked at the end, there was a book by MAKAUT, Elements of Mathematical Ecology. That is a very good book.
Okay, thank you, sir. And
I can just reply him in this message. So MAKAUT is the author,
okay,
and you can check it in. Yeah.
Thank you, sir. Another question from my end, that is uncertainty theory play important role in biomathematical model?
Yes. Uncertainty theory is very much important, because if you want to understand the evolutionary change in the system behavior, and that is a very challenging factor, so you need to incorporate some sort of game theoretic approach. So instead of considering the population, you can think about individual based, and for each individual at each time point, you need to incorporate an uncertainty that whether it will win or lose the game. If they wins, then they will survive. If they lose, they will be deprived. And that kind of situation is mainly responsible for several kind of catastrophic change is observed in the nature. Just for example, coral reef destruction due to tsunami, but it is quite difficult to predict when next tsunami will come and which part of the world it is going to come and what will be the intensity. But it is a very good question. I must appreciate it. There are a couple of literature on this particular aspect, and that is now dealt in the context of ecology. That is called system with evolutionary approach. And recently we completed one work, but till this moment we are not able to convince the reviewers that if we change the functional form, then is it possible to there is a sudden drastic change in the system outcome that may result in as a final outcome, and that is also responsible for such kind of behavior.
Thank you, sir. Thank you for being a part of our FDP program. Thank you, sir.
Thank you.
Now, over to you, Anusha. Anusha? Hello?
Yes, sir.
Please.
Now we move to our next lecture session. Our second speaker, Professor Kushum Dev from the Department of Mathematics of IIT Roorkee. Professor Kushum Dev, an eminent professor and researcher in the field of mathematics. Her area of research interests are the nature-inspired optimization techniques, evolutionary algorithm, parallel computing, soft computing, neural network, and many more things. She has more than 172 research publications in national and international journals. She has received the Best Paper Award in International Conference on Operation Research and Decision Sciences from IIM Visakhapatnam in the year of 2019. She is renowned to us through NPTEL platform for her Operation Research courses. So we are very happy to have her among us today and welcome heartily Professor Kushumdeep Madam to our FDP. Today, her title of lecture is Some Open Problems in Nature Inspired. I request Professor Kushumdeep Madam kindly deliver her speech. Please, Madam.
Thank you so much uh, for this kind introduction. Um, may I first of all wish all of you a very good evening and a warm welcome to my talk. I would take this opportunity to thank the organizers for giving me an opportunity to present my talk. Can you hear me, everybody?
Yes, ma'am. Yes, ma'am.
Yes, Madam.
Okay, thank you. So let me share my screen. It's so nice to see some known names in the chat box and the participation lists. And I'm glad that you got my contact through the NPTEL Operation Research course. In fact, that course is going to run again very soon, this month. So let me share my screen. Um, can you see my screen? Can you
Yes,
see
ma'am.
the
It is visible.
can you see the PPT?
It is still not open.
Just a minute. Hmm, I need to select that window, I think. Let me select that window. Just a minute. Can you see the PPT, the full screen PPT now?
Yes, yes, it comes.
All right then.
Now,
Okay.
now
Yes,
visible.
yes, ma'am. Yes, ma'am.
Yes, yes,
The
visible now.
full form of the PPT. Can you see?
Yes, yes, yes.
Okay. Do I need to lower or up my volume? Is that clear?
Yes, it is clear.
Okay. So off we go. I have 1 hour allocated, and I'll try to finish my presentation during this 1 hour. The topic of my presentation, as has been mentioned, is nature-inspired optimization techniques. I will be talking about the open problems, but before that, we need to understand the fundamentals and the advancements that has taken place in this very important research area, particularly when we want to solve real life problems which are encountered in many different fields of study. This is the flow of my presentation. First of all, I would like to define what exactly do we mean by nature-inspired optimization techniques. And I will share with you some success stories indicating how useful these techniques are. Then I will introduce a general template under which any nature-inspired optimization technique can be implemented. And with the help of a small classroom problem, I will illustrate 3 most commonly available nature-inspired techniques and throwing some light on the applications to real-life problems. I will come to the challenges, that is the open research problems in this area. And then I'll wind up with a comment on the research work at IIT Roorkee with some announcements. So in order to know more about my work, it is convenient to use the Google tools, the researcher ID and the ORCID ID and the Google Scholar ID. So you can just look at my web page for my details. I am not using my camera, so that's the reason I put my picture. First of all, let us understand what exactly do we mean by optimization. Usually, when we are talking about any decision problem, whether it is in our day-to-day life or whether it is in some scientific endeavor, that decision-making problem is actually an optimization problem. So, for example, in this picture, there are two people who want to climb the hill, and there are two paths. They are thinking which one to use. Of course, there is the third path that they can use, which is not exactly a road. So, like this, there could be a number of alternatives for reaching the top of the hill. Therefore, uh, the best strategy which one should adopt for making a decision to reach to the top of the hill is a simple example of optimization. We do it every day. There are numerous examples. We do it every day in our everyday life. We look at certain decisions, whether we want to find a match for our daughter. We look at various options and we want to optimize which match we should settle for. The idea is that we are going to choose the best amongst the various alternative strategies. And this can be seen particularly in simple applications of design of machines. I usually mention that every design problem is an optimization problem. Particularly the design of machines, the design of electronic items, the design of mechanical items, the design of a bridge, the design of a house by an architect, and you name it. See, these are all optimization problems. Also, wherever there is cost involved, that is also an optimization problem because we want to minimize the cost. And of course, whenever we are designing a system, we have to make sure that a system should be as reliable as possible. So any problem consisting of maximization of reliability is an optimization problem. Then comes the situation where we have some kind of experimental data which has to be fitted into the theoretical data. So it's the least square estimators. And these days, we are using neural networks for solving numerous kinds of problems. There again, the optimization of weights is a very challenging problem. Particularly, I would like to mention machine learning. Now, you know that these days machine learning plays an important role in no matter what area you're talking about. For example, the classification of data. There's a huge amount of data that is available. We need to classify it. We need to identify the features. So feature selection, the regression analysis, topology optimization, and the training of neural nets. These are all problems which need a lecture or I would believe a course in itself, you know, and you can just go on and on talking about it. The question is, what are, where are actually nature-inspired algorithms preferred? Why are they preferred over the traditional optimization algorithms? See, you know that the analytical theory is rich about optimization algorithms, particularly the theoretical analysis, that is the Kantaka theory, the Lagrange multiplier theory. And when you are moving to the numerical techniques, then we have the steepest descent method, the Newton-Raphson method, and so on and so forth. So the question is where the nature-inspired algorithms are preferred and why they are preferred. The reason is that the nature-inspired techniques can be applied to non-differentiable functions and to discontinuous functions as well. Also, they can be implemented on non-separable functions, rotation functions, ill-conditioned problems, and not to forget the NP-hard problems, particularly, the NP-hard means the non-polynomial complexity problems where the complexity of the problem increases as the input size or the size of the dimension of the problem increases. So what are the characteristics of real world problems? We need to understand because our objective is to solve real world problems. So usually the real world problems have a non-differentiable function which is to be optimized subject to non-linear and linear constraints. There could be a situation where the search space is discontinuous and maybe discrete, and there could be a situation where the decision variables are of mixed characteristics. That is, some of them are discrete, some of them are continuous, some of them are permutation. Also, the large dimensionality of the problem also creates difficulties. Yeah, multi-objective is a very important aspect of a real life problem. Usually, I feel that most of the real life optimization problems are actually multi-objective in nature. Let's say, for example, you want to buy a car. You want to make sure that the car should be fuel efficient. The car should be of aesthetically looking good design. It should satisfy all the family requirements and so on and so forth. So usually there are a number of optimization objectives which have to be met. And that's the reason why multi-objective optimization problems are important. So the classification of the optimization problems can be done on a number of criteria, as has been mentioned here. The number of decision variables, the type of variables, the degree of the non-linearity of the objective function, the presence of constraints, and the kind of optimas there may exist, that is, whether they are multimodal or unimodal, and again, the number of objective functions, and whether the objective functions change over time. Now, this last line I would like to emphasize. For example, you want to predict, let us say, the financial data, let's say the stock market. Now, this is a ever-changing objective function. That is to say, if you want to predict the market behavior, this is a dynamic. The objective function is dynamic in nature because every moment it is changing. So these kind of problems are really very, very difficult, and the traditional techniques are not able to take care of them. So based on this, usually the classification of the various optimization algorithms is done into the following categories: unconstrained, constraint, multi-objective, multi-solution, dynamic, etc. So this kind of background is available in most of the literature. And those of you who would like to know more about it, you can just look at this. So before we proceed, let us try to define what exactly do we mean by a optimization problem, which is non-linear. You know that the linear programming problems have a simple minimize fx subject to ax less than equal to b kind of stuff. And there is only one kind of solution that itself does the whole thing. There is only one good old simplex method which takes care of the linear case. However, the moment you move to the nonlinear case, things become very complicated, and therefore we need to understand the definition of a nonlinear optimization problem. Usually, the function that has to be minimized or maximized is nonlinear in nature, and it is subject to a number of constraints which can be represented with the help of a set S, where S is a subset of Rn, and we can define this set S using the inequality constraints and the equality constraints. Each of the functions involved, that is f, the g's, and the h's, they could be nonlinear, and each of them could be a function of n variables, where n is greater than or equal to 1. It's a positive integer greater than or equal to 1. Also, it is possible that the inequalities could be m in number, or they could be totally absent, and similarly the equality constraints. Apart from this, there are restrictions on the lower and upper bounds on the decision parameters, which are usually indicated separately. So coming to the solution of the nonlinear optimization problem, usually we say that a point x bar in the feasible region is said to be a local optimum solution, or rather a local minima, if there exists a epsilon neighborhood around x bar such that fx is greater than or equal to fx bar for every x belonging to d intersection n epsilon x bar, where d is the feasible region and n epsilon x bar is a epsilon neighborhood of x bar. In such a condition, x bar is said to be as a local minima. On the other hand, we can define a global minima to be a point x bar belonging to the search space if this condition fx is greater than or equal to fx bar is satisfied for all x in the search space. In order to understand this concept of local and global, let us look at this hypothetical example. Here we have two local minimas and one global minima. Obviously, the global minima is also local, but we have the definition, according to the definition of local minima, a minima is said to be local if it is a minima within an epsilon neighborhood. So all these 3 points are actually local minimas. And the global one is that which is satisfying the condition in the entire search space. Now, apart from this, we also have what are called as the stationary points, which satisfy only the necessary condition, but not the sufficient conditions. Because at the stationary point, the first derivative is equal to 0, but you cannot say anything about the second derivative. In this diagram, I'm trying to illustrate a two-variable problem where we have the first variable along this axis, and the second variable is along this axis. And on the vertical axis, we have the objective function value. And as you can see, there are two local maximas and one global maxima. And also there are two local minimas, one local minima and one global minima. So this is an illustration to indicate what exactly do we mean by local and global solutions. Coming to the mathematical complexities, people have designed a number of mathematically complex functions which can demonstrate the various kind of complexities that might arise in a simple optimization problem. Here, this is the Eclay problem. It's very famous. It's an n-dimensional problem. As you can see, this n is a positive integer greater than or equal to 1. And the complexity of the problem increases as and how n is increasing. So n can be 1, n can be 10, n could be 10 lakhs. And as and how the value of n increases, the complexity of the problem also increases. If you look at the two-dimensional situation for this Eclay problem, this is what the hypersurface of the objective function looks like. Second problem is called the Grivant problem. It has the similar behavior. These kind of problems are called the scalable problems because we can scale them, and when we scale their dimension, then the complexity increases. Another problem is the restringent problem. This is also having a very complex kind of a hypersurface. And then comes the Rosenrock problem. This problem has a different kind of complexity. It is a unimodal problem, means there is only one minima, that itself is the local and that itself is the global. And actually it consists of saddle point. So there is a saddle point, the one I showed you, which satisfies the necessary condition but not the sufficient conditions. This is the two-dimensional case, but in general it could be increased for any value of n. And finally, the Sheffel function. This also has a very peculiar kind of hypersurface. Like this, the literature is rich about a number of optimization problems which have different kind of complexities arising into them. And we are supposed to design optimization algorithms so that we can solve these problems. Apart from the mathematical complexities and the mathematical functions, we are also interested in solving real life application problems arising in various areas of study. So we perform a developmental design, keeping in view the evolutionary design, the co-evolutionary design, and finally we come up with a emergent design. So this is a design process that has to be adopted for designing a computational algorithm. The objective, as I said, is to make sure that we satisfy the real life problem in a fashion where the robustness, the novelty, the optimality, and security of the algorithm is obtained. Coming to the literature review for the numerical techniques is concerned. Please note, I'm only talking about the numerical techniques. There are two kinds of approaches. First is called the deterministic approach and second is called the probabilistic approach. In the deterministic approach, we have a number of methods. For example, the steepest descent method, the Newton-Raphson method, and so on. And in the probabilistic methods, this is a list of some of them, and this is the focus of my research. We have genetic algorithms, particle swarm, etc. The difference between the two is that in the deterministic approach, we have fixed transition rules, which are applied iteration over iteration until and unless the convergence takes place. And we begin with the initial guess and approximate that initial guess over and over again in the generations or the iterations. On the other hand, in the probabilistic approach, instead of working with one solution, one initial guess, we work with a randomly generated feasible solution, a set of them, not one, but many of them. These are randomly generated in the search space, and at each iteration or each generation, they are updated using some kind of a probabilistic formula. By probabilistic formula, we mean a formula which incorporates some kind of random numbers. Therefore, let us understand the definition of nature-inspired optimization techniques. These are those techniques which derive their inspiration from some natural phenomena. And as and how we proceed, we will see that there are many such algorithms under this category. This is a partial list of some of the nature-inspired optimization techniques. They're also called heuristics because they learn from their behavior, their previous behavior. So at every generation, they perform some analysis, and based on that, they proceed to the next generation. We can classify these nature-inspired techniques where there are some overlaps, which is shown here in this diagram. So as I said, the difference between the nature-inspired techniques and the traditional techniques has to be understood, and then only we can appreciate why we are interested in studying the nature-inspired techniques. Usually, the nature-inspired techniques search from a population of solutions instead of a single solution. Now, this needs to be understood carefully. Suppose we have a hypothetical function, we want to minimize it. We know that the minima is at xk plus 1. So what we do is we start with a initial approximation. We call it as x naught, and this x naught is updated at each iteration. So we go from x naught, x1, x2 like this, and we reach xk plus 1 in a convergence sense. Some of the categories, some of the algorithms in this category is the Newton-Raphson method, the steepest descent method, and so on. Many such. There is, in fact, in Roorkee, we teach a course on these kind of numerical techniques. And this is the way usually the deterministic techniques work. On the other hand, the probabilistic techniques, they work like this, in the sense that instead of one solution, we generate 3 solutions. Now, why 3? It's not really necessary that we generate 3. Maybe we could generate 4 also. So we generate 3 solutions and evaluate the objective function at each of these 3 solutions, as is shown here, x0, x1, and x2. And at each generation, we do some, we apply some operators which depend upon the particular nature-inspired technique that we are talking about. And once we apply these operators, we get another population. This is the initial population. Once we apply those operators, we get another population, which is called as the next iteration or the next generation. Like this, we repeatedly apply many generations over and over again till all the solutions, all the feasible solutions, they converge to the minimum. For example, in the next population, the points have taken a new position. They have occupied a new position. Like this, at every population, every next population, these points will keep on converging closer and closer. Another way to understand this is using this graph. Suppose we have a 2-variable problem, x versus y, and we have a red point indicating the global minima. We generate a sample of 10 randomly generated feasible solutions in the search space, and we keep on applying the operators of the nature-inspired technique, and we find that at each generation, these points, they come closer and closer until finally they are clustered near the global minimum. Now, this kind of exercise can be very easily implemented on the computer with the help of good computers available. The other differences are that instead of the deterministic rules, we use the probabilistic transition rules, which will depend upon the particular nature-inspired technique that we are talking about. And also the advantage is that they can be applied to discontinuous and non-differentiable functions. And usually they are very easy to program, and you can implement them on the computer the way you like. The classification of the evolution of the nature-inspired algorithms is done into 4 categories. First is the evolutionary algorithms, swarm intelligence, algorithms based on the physical laws, and finally the miscellaneous ones. In the first category, we have the following algorithms, that is genetic algorithms, differential evolution, evolutionary strategies, and genetic programming. These algorithms derive their inspiration from the Darwin's theory of evolution, which means that there are 2 properties of this Darwin's theory of evolution. First one is the inheritance, and second one is the competition. Inheritance means that the good features or the good traits of the kth generation should be passed on to the next generation by giving priority to those who are having high fitness. This is the normal way every evolutionary algorithm works. Then comes the success stories. Now, as I mentioned, uh, the evolutionary algorithms have been implemented in a number of real life problems. And I am pleased to tell you that genetic algorithms was used for the design of bullet trains, the nose of the bullet train, for the high-speed bullet trains. This is mentioned in a Japanese website, which clearly mentions that genetic algorithm was used not only for the development of airplane wings, but also for the railway rolling stock and the nose shape of a bullet train, keeping in mind the optimal aerodynamic performance. Imagine this is a highly complex problem, and the traditional techniques cannot solve it. So that's the reason why genetic algorithm was employed. Second category is the swarm intelligence based algorithms. These are the some of the algorithms under this category. A swarm means a group, and intelligent means those uh, particles in the swarm which have an intelligent behavior. What is the meaning of the intelligent behavior? It means, yeah, so there is a small question in the chat box. A simple question is raised from my side for my clearance. What is the difference between GA and genetic programming? Oh, thank you so much. That is a very good question. Let me reply to that. Let me go back to the genetic programming. Yeah. So usually in genetic algorithms, we talk about chromosomes, and each of the chromosomes are carried over to the next generation using the crossover operator and the mutation operator. Okay. Usually these chromosomes are supposed to represent feasible solutions of an optimization problem or a search problem. Now the genetic programming talks about the same concept, but there in genetic programming, we have, uh, instead of the feasible solutions, we have programs, computer programs, full-fledged computer programs. And the subsequent operators are applied on these computer programs. So there is a crossover operator which is applied on the computer program. So suppose there are 10 computer programs. Out of those 10 computer programs, a crossover operator will be applied on some of them which are having high fitness. And fitness is a concept which is defined due to certain particular criteria. In other words, to put it briefly, the difference between genetic algorithms and genetic programming is that in genetic algorithms, we work with chromosomes which are feasible solutions of an optimization problem. Whereas in genetic programming, we work with computer programs for a particular problem. So this actually, the genetic programming itself is a very, very large area of study. So thank you for this question. And now let's move on. So I was talking about this. Okay, one more question. Okay, so I have answered this. The swarm intelligence algorithms are those algorithms which mimic the behavior of birds who fly in the search space, or fish who swim in the pond. This is the collective behavior of non-intelligent creatures. By non-intelligent, I mean non-intelligent with respect to human beings. But they are intelligent because they do not collide amongst each other. They do not leave the group, and they all move to the same direction. So this is what is called as a swarm behavior. And that's why it's called as an intelligent. And the swarm intelligence algorithms, there are many of them. This is just a partial list of them. Then the third category talks about those algorithms which derive their inspiration from some kind of a physical laws, for example, the gravitational search and the central force optimization. Gravitational search algorithm uses the concept of gravity, and the CFO uses the concept of the attraction between every particle which exists on this earth. And finally, the miscellaneous category talks about harmony search algorithm, which is a music based algorithm. Biogeography based optimization is an algorithm which is based on the immigration and emigration of habitats. Similarly, the sine cosine algorithm talks about the behavior of the sine and cosine. And like this, there are many other algorithms which do not fall into the first three categories. A brief historical development about these nature inspired algorithms is the Monte Carlo simulation, which was just a simple algorithm where the solutions were randomly generated, and later on came the random search technique, which had two phases. In the first phase, the objective function was evaluated at a number of randomly generated feasible solutions, and at the second phase these solutions were manipulated by local search till a possible candidate for an optima is obtained, and this process was repeated over and over again. Then came the ant colony optimization. It is a very famous algorithm. It mimics the behavior of ants who travel from the food source to the nest, and they follow each other. How do they follow each other? There is a communication taking place amongst each of these ants based on a pheromone. Pheromone is a scent which is excreted by the bees, and this is responsible for telling the follower where you have to come, how you have to follow me. The ants are so intelligent that as and how an obstacle comes into its way, they take a decision that they have to use the shortest path. And this decision is done again with the help of this intelligent ants. So based on this, the ant colony optimization was developed, and even today it is finding popularity in many discrete problems, particularly the traveling salesman problem, etc. So genetic algorithm, as I said, Holland is called the father of genetic algorithms, and it is based on the Darwin's theory of evolution, as I mentioned. It is actually a process which mimics life on this earth. As you know that the life on this earth began with a single cell, and slowly over and over the millions and millions of years passed by, and we are now at the stage of human beings, and maybe after billions of years later we will become superhuman beings. So what does one particular cycle of a genetic algorithm looks like? Because genetic algorithm is the basic structure or the basic nature inspired, or I would say the most popular and most versatile nature inspired technique. So I want to throw some light on this. Here in one cycle, we generate an initial population which consists of randomly generated feasible solution indicating the various colors, meaning that each feasible solution is having different centers and different radii. And each of these randomly generated feasible solutions are evaluated using some kind of a fitness criteria. And out of this fitness test, some parents are selected. So this is a subpopulation of the initial population. And on this selected parents, the various operators are applied. The crossover operator, and children are produced, and then a mutation operator is applied, and we get a new population. With this one particular cycle of a GA, we can repeatedly apply this cycle in the form of this flowchart. That is, generate initial population, evaluate the objective function, apply the crossover mutation, etc., and repeat till the stopping criteria is satisfied. The idea is the natural selection, the struggle of life. They say that even in today's pandemic situation, they say that those human beings who have high immunity, they are likely to survive and the rest of us might die. So this is the concept of natural selection. You know, there is always a continuous struggle for life, and all those who are fit will survive, rest of us will die. So the same concept is implemented in the case of genetic algorithms. As I said, that GAs are adaptive and they learn from experience. By adaptive, I mean, depending upon the problem at hand, they can learn from their experience, and they are very effective to solve complex problems, as I mentioned. These are the operators of a standard genetic algorithm. Every genetic algorithm has to be encoded into the search space, whether it is a binary space or it is a real space or it is a permutation stage, whatever the encoding formula that has to be implemented. This is a one-time operator. The other operators are the repetitive operators which are applied over and over again. So there are a number of selection operators, for example, the tournament selection, which is exactly the same way in which many teams are participating in a tournament. From each pair of, like I say, individuals, a tournament is played and the best one is selected into the mating pool, so that this mating pool can be used for applying the other crossover and mutation operators. Similarly, the roulette wheel selection is also a very popular method for choosing which chromosomes should participate in the next operators. Similarly, there are many kinds of crossovers, of course, depending upon the encoding, whether it's binary encoding or it is real encoding, and there are other encodings as well. And like that, there is also an operator which is called as the mutation operator. This mutation operator also depends upon the kind of encoding. So in general, we can define a pseudocode of a GA like this: generate an initial population, and till the stopping criteria is not satisfied, keep on applying the standard GA operators and keep on creating a new population at each generation. Then comes the real coded genetic algorithm operators. These are very important, and my initial work is focused on the design of new crossover and mutation operators, specially designed for real coded genetic algorithm operators. Then comes the memetic algorithms, which are actually hybridized genetic algorithms because they incorporate some kind of a local search in the genetic algorithm. The idea is to improve the performance of GA, although it might be at a higher cost because the computational requirement will increase. The way in which the local search can be implemented can be done in many ways. Either it is at the initial population stage or it is after the crossover and mutation operators are applied. Then comes the self-organizing migrating genetic algorithm. These algorithms are based on the self-organizing patterns appearing in nature, particularly flowers and so on. Now coming to the swarm intelligence, after this, we need to look at the swarm intelligence behavior. As I mentioned, that swarm intelligence is a behavior which mimics the birds who fly in the evening from wherever they are. They collectively fly. So it's a collective behavior. Now I have a small video to illustrate what exactly do I mean by this. On this tree, you will notice that there are many birds who are sitting. And you will find that the moment I click, all these birds, they will fly in different directions. However, very soon they will interact amongst each other and they will all start moving in the right direction. So please watch this video carefully. It's a 2 minutes clip. You will notice that initially they fly in different directions, but sooner or later they realize that we will move in the right direction, towards the right. So please look at this video. So this is an intelligent behavior that all the birds are flying together. Earlier they were flying in the wrong direction. Then some communication occurred between them and they all started flying in the right direction. Another small example for the swarm behavior is illustrated in this video. So this is also a swarm behavior. All these birds are crossing the signal. Some kind of communication is taking place between them. And this is what exactly we are going to implement into our particle swarm optimization algorithm, where all the search agents in the search space will be asked to move in a particular direction, because that is the point of attraction, that is the point of minima. Coming to the success stories, you must have heard about the drones. Drones play an important role not only in defense, but also in surveillance, in flood hit areas, and so on, many applications. So swarm drones is a group of drones who work on the principle of swarm behavior. They collectively take decision. I'm just going to play another video. So usually in the beginning, they might fly in different directions, but very soon the communication takes place between them and they all move to the target. Now, in order to understand all these nature-inspired techniques, let's take a simple two-variable problem. We all know that the minima is at the origin. However, in order to understand the working of these algorithms, I've chosen a simple classroom problem where x1 and x2 have different bounds specified. The general template of a nature-inspired optimization algorithm is like this, that we are going to generate a population of randomly generated feasible solutions in the search space, evaluate the objective function, and begin the iterations. We will employ a big for loop where iteration goes from 1 to maximum number of iterations allowed. So maximum number of iterations allowed is a parameter which we have to specify in the beginning of the algorithm, and then perform the operators based on the choice of your nature inspired technique. And once this for loop is over, whatever best solution you have, that is reported as the optimum solution. So this simple template is going to help us get the nature inspired technique working. So first thing is how to generate an initial population. For this, we will generate uniformly distributed random numbers between 0 and 1. This is usually available in most of the computer programming languages. And then we need to scale it between the lower and upper bound, which is given to us. So capital R is going to be x minimum plus R times x max minus x minimum. This will give me a random number R, capital R, between x minimum and x maximum. Although there may be a function or a library which will be helping you to generate a random number R between x min and x max, but in principle, that is the way the scaling has to be done between lower and upper bound. As an example, suppose we have a random number R 0.16345. I'll apply this simple linear transformation and I'll get capital R as minus 67.31. So this is a number, capital R is a number between minus 100 and 100. And similarly for the second quadrant, for the second coordinate, I have generated R is equal to 0.69012. And then I'll scale it between minus 1 and 50. So I get this number. Like this, I have got the first feasible solution and I can create the entire population using this methodology. Next comes the evaluation of the objective function. All you need to do is substitute this into the objective function. Our objective function is x1 squared plus x2 squared. We'll just put it here, and we'll repeat this for the entire population, and maybe we can later on sort them according to their objective function value. And then we apply the various operators that we want to consider. All right, so what I'm going to do is I'm going to use these some of the algorithms which I mentioned, and I'm going to illustrate how the behavior of this nature-inspired technique works. There are many ways in which the stopping criteria can be performed. The most common one is the maximum number of predefined maximum iterations. And there are others also, which I have listed here. So this working example I will perform with the help of these three commonly available nature-inspired technique. The first one is the PSO, the particle swarm optimization. We have to generate a swarm and evaluate their fitness. And each particle or each feasible solution will record its fitness. Accordingly, the global best, the personal best, and the velocity has to be modified using the two governing equations of the particle swarm optimization. This is the first equation, which is called the velocity update equation. It's a linear equation which is responsible for updating the velocity of every particle in the search space. Here you will notice the P best is called the personal best, means it is the personal best of every particle over history, that is from the day it started in the 0th iteration. And global best is the overall best of the swarm for all the particles in the swarm. And the current is the for each of the particles. C1 and C2 are certain constants which have been theoretically proved to satisfy some conditions. R1 and R2 are random numbers uniformly distributed between 0 and 1. And like this, we have the position update equation. So these two equations, they are responsible for the PSO algorithm. Now coming back to our problem, I have generated a population of 6 randomly generated solutions. Please note that I have chosen them to be integers. Actually, they could be real numbers also, but just for the ease of my calculations, I have chosen them to be integers because I want to see how it works. So this is a classroom problem, and I find that the third particle is giving me the best. That's why I'm calling it as global best, G best. Now I'll apply the velocity equation and the position update equation for each of the 6 particles. So for the first particle, this is what I get. Similarly, for the second, third, fourth, fifth particle, this is what I get. And this is the table which I get after the first iteration, which means that the third particle has now got a fitness 1.37. Please appreciate that we started from 2 and now we have come to 1.37. This is only one iteration. Like this, if we keep on applying more and more iterations, we'll keep on getting better and better results. Look at this second iteration. We have got 0.13. So 0.13 is all the more better. The second algorithm I'm talking about is the Gray-Wolf algorithm, which is an algorithm which mimics the hierarchical behavior of gray wolves, where the best is called the alpha wolf, second best is called the beta, and third is called the delta, and the remaining them are called the omegas. So the gray wolf, they want to attack a prey. For this, they have to employ the encircling behavior. For this encircling behavior, this is the mathematical model. Then comes the hunting behavior, which is shown with the help of these mathematical equations. And finally, the attacking. So with these 3 set of equations, we can look at the generalized pseudocode of a Gray-Wolf optimization algorithm like this. And I will use the same population to apply the gray wolf optimization algorithm. And as you know that the second, the third one, sorry, the third wolf, in this case, we call it as a wolf, not a particle, we call it as a wolf. The third wolf is the best. That's why it's called alpha. We will apply the first iteration. These are the calculations I have shown. And when we move on to the uh, updated wolf, the first updated wolf, this is what is obtained. Like this, we get the other updated wolves. We get the first iteration 0.012. Look at the objective function. From 2, it has jumped to 0.012. How remarkable. Please note, we are using only 6 wolves. Suppose we increase this number, we are likely to get better convergence and faster convergence. Then comes the second iteration. And this is the, we find in the second iteration, there is no improvement. But there are many reasons for this. The third algorithm that I'm going to talk about is the artificial bee colony algorithm. It was developed by Karaboga in 2005. It mimics the honeybees, the the two properties of honeybees, that is the self-organization and division of labor. There are 3 kinds of components of this ABC: the food source, the employed foragers, and the unemployed foragers. So each of the forager is that bee who is hunting for food, uh, and there are the other ones who are just sitting and doing nothing. So the objective of each of these foragers is shown here. As I said, forager is the process of finding food. In order to find the food, these bees, they perform an activity which is called as a dance. And the way in which this dance works, it tells the other bees, where to go in the search space. So there are there is the round dance, the waggle dance, the tremble dance. Accordingly, according to this dance, the bees communicate to the others where we have to go for in search of food. It is a small video again to show you how the communication takes place between the bees. So you see, this is the way the communication takes place between the bees, and this is implemented in the artificial bee colony algorithm, where there are 3 types of bees which perform their own allocated task. And this is a cycle of one cycle of the honeybees social behavior. And we will be implementing our example using this ABC algorithm. So as you know that this is the same population I have chosen. This third B is the best. Here we are not calling it particle. We are calling it as B. So the third B is showing me the best. And now I will apply the ABC algorithm. I don't have time to go into the details of the calculation. So what I will note is after the employed B phase, this is what get after the first cycle. So after the first cycle, I get 0.0362. That is a big jump. Similarly, I get 0.0362 after the cycle 2. Therefore, now let us try to analyze the behavior of all these three algorithms in a comparative fashion. So the first metric of comparison is the fitness of the best solution. How fit each of the best solution is in each of the three algorithms. This is a comparative analysis as far as 0, 1, 2 iteration is concerned. Also, we can compare this performance of the worst solution. And this is what the comparison looks like. Another methodology for comparison is to look at the search space. Now, this is the search space. In the beginning, it was same at the 0th iteration or the initial iteration. However, as and how we move to the first and second iteration, this is the behavior of each of them. What do we find? We find that under gray wolf optimization, all the points have clustered very close to each other. But this is not all. The question is, which algorithm should be chosen to be the best? The answer to this lies that there is a no free lunch theorem, which was proposed by Wilpred and McCarty, which says that there is no meta-heuristic algorithm which is best suited for solving all optimization problems of varied complexities. Just like you cannot have one single medicine for all diseases. Say, if you have a heart problem, you have to eat different kind of medicine. If you have a diabetic problem, then you have to eat different kind of medicine. So exactly in the same way, for every optimization problem which has a varied kind of complexity, there cannot be one standardized heuristic algorithm which will solve all kinds of complexities, because the complexities in the optimization problems is very, very varied. Okay, there is a question in the chat box. Can we implement TSP type optimization problems using gray wolf optimization? Oh yes, of course, definitely. Yes, you can do that because TSP, in fact, one of my student currently is working on colored transportation problem using gray wolf optimization. And definitely it can be done. Sure, it can be done. All right. Now we come to the end of this talk, and I think I'm taking some, I'll need just 2 or 3 minutes more. I will be giving you the open challenges. The first open problem is how to analyze the nature-inspired techniques mathematically in terms of their convergence, stability, and robustness. Because till today, there is no real mathematical rigorous proof for the convergence of these algorithms. And therefore, we need a thorough study mathematically to analyze their convergence and stability and robustness. Second open problem is fine-tuning the parameters of a given algorithm so as to achieve its best performance for a given set of problems. Now, as I said, the no free lunch theorem says that there is no single algorithm which will solve all kinds of problems of varied kinds of complexities, but at least we can divide all the problems in different sets of problems so that we can fine-tune the parameters and recommend that these are the fine-tuned parameters which will give you the best performance. So this is a big challenge. The third problem is to design new type of benchmarking optimization problems. As I showed you, there are so many benchmarking problems, but still, the research is open where you can design new optimization problems. The fourth open problem is to identify the most suitable performance matrices for a fair comparison of algorithms. I have just taken a simple example in this lecture, and I use the best solution, the worst solution, and the search space. I use these three parameters uh, to evaluate the performance of the algorithms. However, we need to identify more and more suitable performance matrices for the purpose of comparison. And finally, how we should scale up the algorithms so that we can solve the large scale problems, particularly when we want to solve real world applications. So I would like to invite all of you to look at my research work at IIT Roorkee. These are my past students who have worked on genetic algorithms. Currently, they are now employed at various different locations all over the world. And then there were some students who worked on particle swarm optimization. They are also placed at very good institutes. And then there are 20 students who have done their PhD with me. And particularly, I would like to mention Dr. Amrik Singh, who was the deputy director, who is the deputy director of DRDO. He worked for his PhD under my supervision using artificial bee colony algorithm. And like this, all of them are good, but this particularly I would like to mention about Amrik Singh because he used artificial bee colony algorithm for solving the avalanche forecasting problem in DRDO. And I am happy to inform you that this tool that we developed in his thesis is being implemented in DRDO today. And I am very proud for this small contribution towards the nation. All right, then, okay, then comes the current students. They are all working in different areas. Karuna Pawar is actually working in the traveling salesman problem, which I just now answered. And other students are also working in various kinds of problems. I have written a book on nature-inspired optimization and introduction. It is in press and will be out very soon. And usually I recommend another very interesting book with one of my, it has been written by one of my very good friend, Xinxi Yang. And in fact, I'm planning to organize an international short-term course, a winter course on nature-inspired optimization, where we're going to talk about hands-on experience, how you can actually learn the use of nature-inspired techniques. And Professor Xinxi Yang is going to be one of the speakers of this short-term winter school. These are some of the journals where you can see lots of good publications. And of course, there are a number of conferences also available. Finally, these are some announcements I would like to make. I am the president of the Soft Computing Research Society, whose objective is to, it's a non-profit organization. Its objective is to inculcate the concept of soft computing into the society. We sponsor, faculty members and research scholars to attend conferences and workshops. And also we give the funding for organizing FDPs. One of the signature events of the society is the conference of which I'm one of the general chairs. This is in collaboration with Liverpool Hope University, where I'm a visiting professor. One of this conference was held in Liverpool Hope University in 2019. And this year it's going to be held at IIT Indore. Of course, it is going to be virtual because of the pandemic. I am the executive editor of the International Journal of Swarm Intelligence. So if you have research publication, you're welcome to submit your publication there. And finally, I am one of the series editor of the Algorithms for Intelligent Systems, which is a Springer book series You are invited to submit your proposals in the form of monographs and books and conference proceedings. So with this, I come to the end of my presentation, and I would be happy to answer any questions which the audience would be having in their minds. So it's over to you, please.
So much, madam, for such a nice presentation. Uh, Optimization is the art of selecting the best alternative among a given set of options. You started your lecture just showing a well-known real-life game problem, which is very much helpful for our participants to understand the optimization problem that arises everywhere, also almost all the fields of science, engineering, finance, and industry. But your main target to discuss some nature-inspired optimization problem. And uh, in your lecture also, you gave us some examples that genetic algorithm used to make the nose strip of high-speed bullet train, the swarm behavior agent, the swarm optimization algorithm, etc. So thank you so much for your nice presentation. Now I request our member Dr. Shankar Prasad Montal sir to take up the question answer session. Sir, please.
Thank you, Dr. Kushanti madam, for being a part of our 5 days faculty development program. You give a nice presentation. Thank you, madam. And here is some question.
Thank you so much. Yeah, any questions? I'll be very happy to answer.
Yes, ma'am. Some question is
okay,
there.
Okay, there is one question. It says, what is fine-tuning for evolutionary algorithms? All right, that's a very good question. Actually, you see, all the evolutionary algorithms and all the nature-inspired algorithms, they are actually mm, uh, stochastic algorithms. You know, they are using some kind of parameters, as I have just now illustrated in my talk. Now, these parameters have to be fine-tuned for a given class of functions. And it is, as I said, one of the open problems. It's a challenge how to fine-tune those parameters. So this is an open challenge.
Okay.
Any other questions, please?
Ma'am?
Yeah, any other questions?
A participant asked, which one is the best programming language to implement bio-inspired algorithm?
Oh, no, there is no question of best. You can use any language you like. It's absolutely not an issue, because although there are, you can use MATLAB also, you can use Python, you can use C and C++, whatever you like. There is no restriction on the language. It's totally up to your convenience.
Okay. Thank you, ma'am. Next question is, in hybrid optimization algorithm, which factors must be taken into better consideration?
Yeah. Now, hybridization itself is a very vast area, because you can, let us say, you can hybridize, for example, two algorithms in many ways. Let me give an illustration. Suppose you want to hybridize a GA and a PSO. Okay. So one way is you divide the initial population into two halves. Okay. And apply the GA operators on first half and apply the PSO operators on the second half, and keep on doing this in the entire process of the algorithm. Another way is how to choose those half, whether it is randomly chosen or whether it is chosen according to the fitness, according to the objective function. That is one thing. Another way of hybridizing could be that at each alternative iteration, you apply different operators, different algorithms. For example, you apply GA in the odd iterations, and then you apply PSO in the even iterations, the odd even kind of a scenario. So like this, hybridization itself is a very big area of research, and you can hybridize not only two algorithms, you can hybridize more than two algorithms the way you like. So this is a very lucrative area for research.
Thank you, madam. And another question is from Professor Shobhan Roy, that what is the difference between genetic algorithm and genetic programming?
I have already replied to that. Genetic algorithm and genetic programming, they are two different things. Genetic algorithms is working on feasible solutions, whereas genetic programming is working on computer programs. So the crossover, the mutation operators that are applied on the feasible solutions is done in GA, and if the crossover and mutation operator is done on the computer programs, then it is called genetic programming. So each of them are different concepts.
Thank you. Another question is, ma'am, how Lingo or Cplex like software work? Is it use nature-inspired algorithm in backend?
No, not to my knowledge. Lindo and Lingo, they are using deterministic techniques. They do not use any nature-inspired techniques. And in fact, the MATLAB toolbox has a toolbox which is called as a genetic algorithm toolbox. Similarly, it has a PSO toolbox. But usually I'm not very happy to use these toolbox because, these toolboxes are black boxes. What kind of PSO is being implemented, you don't know that. Because PSO, there are many kinds of PSOs as well. If you look at the literature, there are many kinds of PSO. For example, the global PSO, the local best PSO, off-the-shelf PSO, and many other variations. So which is being used in MATLAB is not known. And another thing is, suppose you want to make any changes according to your problem at hand, you cannot make that changes in that MATLAB toolbox. So that's the reason why I'm not very happy with using a black box. And usually I suggest to my students, you please write your own code, and you can just then freely make changes in the code that you have written.
Thank you, madam. Another question is, which nature-inspired algorithm is best?
That is the question I replied over here in the no free lunch theorem. This is a very important concept which says that just as you cannot have one medicine for all diseases, similarly, you cannot have one algorithm which will be best suited for all optimization problems, because the nonlinear optimization problems are all having different kinds of complexities, as I illustrated in the beginning of my talk. So you cannot say that this algorithm is the best for all optimization problems.
Thank you, madam. Another question is, after consideration of present day status, what is the future application of nature-inspired algorithm?
Oh, the sky is the limit, I would say. The sky is the limit.
Yes, ma'am. Yes.
There are lots and lots of applications. You just need to look at the literature. I mean, people are trying to apply nature-inspired optimization in any and every sphere of human activity, where you can take decisions and it becomes an optimization problem. Financial, for example, financial forecasting, it has it is using optimization, nature-inspired optimization techniques. Then there is, as I said, forecasting of earthquakes, forecasting of landslides. Similarly, the design of chip in computer science. You just name it, and applications are there. Okay, there is one more question in the chat box. How can we choose evolutionary algorithms for different types of optimization problem? Yeah, this is what I replied. No, I replied that this is the no free lunch theorem. It is called the NFL theorem. The NFL theorem says that it is still a challenge.
Okay. Thank
Yeah.
you, madam, once again for being a part of our FDP program. Thank you, madam.
Thank you so much for inviting me, and wish you all the best. And I'm happy to stay in touch with any of the participants who would like to contact me. You can just look at my website for you know for getting hold of my email. There it is. So you can look at my email, and you can just drop me a mail, and I'll be very happy to get in touch with you. Thank you so much for being a wonderful audience. Thank you so
Thank you,
much.
ma'am. Thank
And thank you for the inviting me here. Thank you.
you.
Thank you, madam.
Thank you.
Now, to move on our next session, we will take a 5-minute break and our next speaker will join at 6:50 p.m. So we'll be back at 6:55 p.m. And so please stay connected with us and thank you.
Welcome back to our program. Um, Let us start our next session, lecturing session. Our next speaker has already joined. So let us start our next session. Um, Professor Binayak S. Chaudhary, he is the last speaker for today. He is from Mathematics Department of IST Shibpur. Professor Chaudhary is an eminent professor and researcher in our country in mathematics field. His area of research ranges from functional analysis, topology to various fields of applied mathematics such as theory of relativity and cosmology, quantum information theory, nonlinear dynamics, chaos, quantum communications, and theory of optimization. He has more than 250 research articles published in various reputed journals in areas of pure and applied mathematics, theoretical physics, and decision science. He has guided more than 17 PhD students so far. We are very fortunate enough to have him among us today. We cordially welcome Professor Chaudhary to our FDP program. Today his title of lecture is Introduction to Quantum Communication Theory. I earnestly request Professor Chaudhary kindly to start his speech. Sir, please.
Good afternoon. Am I audible?
Yes, sir.
Yes, sir.
Okay. Good afternoon. Let me begin by extending my thanks to the organizers for their invitation for delivering this lecture in front of all of you. So let me directly go to the subject matter by sharing the screen. Okay. This is introductory quantum communication theory. I think the audience is largely from mathematics background, is it?
Yes, sir. Yes, sir.
Okay. Sometimes the link fails, and I will time to time just verify whether I am getting audible or not, because I had such experiences that I go on talking and no one is able to hear. That is the, I should say, dilemma or characteristic, what you say, of the online system. Anyway, so we so quantum communication theory actually falls within the broader domain of quantum technology. If we look at the development of the technology over the years, over 2,500 years or 3,000 years, and we must recognize that the recorded human history is limited by an upper bound of 7,000 years if we are to just evade any controversy over that. And across that time, the technology developed, and mainly mechanical technology was there. And the development was very slow. As you can see, that in the sailing of ships, The ships were made of the same technology, some in the year AD 100 and also in the year AD 1100 down to AD 1700. So the mechanical technology developed after that up to the 20th century. Then what happened? Suddenly we discovered the electrical technology. That means we could know that there is something like electric charge, and this can be harnessed and used to our convenience. Actually, technology is that we harness something and make it use as per our convenience, as per our requirement. That is technology. And then came the splendor of electrical technology. In this era, whatever we see all around is the contribution of electrical technology. It began with the glowing of the lamp, and then blowing of the fan, and then to TVs, and then to other electronic devices. Meanwhile, the telephonic operation was possible. Then the mobile operation was possible. Now the electrical technology had one branching which is called electronic technology, and then there is the power electronics and like that. Now with the help of electrical technology, it seems to be so powerful that we can have something which is remote controlling, and remote control is developed to that extent that we can remotely control some spaceship to the surface of Mars and then make it land, then just make a robot or robotic hand out of that spaceship. Then by stretching the robotic hand, we can collect the some stone of the Mars and then put it back in our spaceship, and then just put that stone back in some space station, which is whirling, just moving around the Earth. All this is possible with the help of the electrical technology. But by the end of the 20th century, that is in the closing decade of the 20th century, the human being recognized that a further, I should say, revolution of technology is possible with the help, which can be called quantum technology, because it is possible with the help of quantum physics rather than the electromagnetic physics. So this is the subject on which rather I should say quantum communication technology is a part of that quantum technology. Quantum technology is more pervasive. It has many aspects. Anyway, quantum mechanics, let me get back to the development of quantum mechanics. The story began in the first quarter of the 20th century. The physics was then facing a great crisis. And it is with the help of the quantum ideas. Why we call it quantum? Because essentially a discretization procedure was laid out to solve certain riddles. And with the help of these quantum ideas, some new mechanics came into being, which is called quantum mechanics. It had some ideas, it had some implications which were not understood and not understandable even with the ideas which were prevailing at that point of time in physics circles. And these ideas were essentially regarding the mechanical, that is Newtonian mechanics, and also the Maxwell's electromagnetic theory, which we were talking of regarding its implications in technology. Now, the quantum mechanics further developed. It paved the way of understanding in a very, I should say, in a very splendid way, of the underlying microscopic world. That is the world which we cannot see, we cannot have a direct perception of that. It is not an atomic world, sometimes it is a subatomic world, what is happening within the nucleus. We see some entities which we call the particles there in the nucleus. We enter into the particles. Then quantum mechanics joins hand with relativity, the another branch of human endeavor in science, which gave revolutionary corrections to our understanding of nature and now is an integral part of that understanding of nature, which at least we are familiar with at this point of history. Then came the quantum field theory. It was further extended, quantum, that is which we call string theory. That is the quantum idea being compiled with the idea of the theory of general relativity, having strong implications regarding our questions on subjects of cosmology or like that. But in the whole sequence, one aspect was particularly neglected, I should say not neglected, but not explored. That is, quantum mechanics can be used in technologies related to communication science. This was not until in 1993. I am giving the reference of the paper. This is one of the, I should say, the basic paper and the paper which can be described as the genesis of quantum communication science. It was published only in 1993. But so great was the impact of this paper that within a course of, within a course of 15 years or like that, the American Physical Society recognized it as a developing and as a promising branch of science as well as of technology, and opened new sections in their publications, new corners for papers in this particular field. Now, what it is actually? To some events which took place in the intervening time. But first, let us go. What is the difference between the classical theory of communication and the quantum theory of communication? Is my link working? I am audible? Hello? Am I audible? Hello? Hello? Am I audible?
Yes, sir, you're perfectly audible.
Okay. I'm confirming. I will confirm from time to time.
Yeah, no problem, sir.
Please respond for that. So, in classical communication, and you know that in the 1940s, possibly I remember it is in 1948, that the mathematical theory of communication by Shannon, this was the basic paper. And it used as basic, it actually, this is not used there, but subsequently as an offshoot of the paper, we now know that the basic basic unit of classical communication is bit. That is, it is given by two numbers, 0 and 1. We all know that. And we encode our message using 0 and 1. There are several ways of encoding and decoding and preserving the encoding against the hackers and etc. etc. In this way, classical that is classical code is a very large chapter of computer science as well as of mathematics and of applied mathematics. But in quantum communication, what we do by taking advantage of the quantum ideas, we introduce two states, 0 and 1. These are Kate vectors and they become parts of a linear space. We allow the linear superposition between 0 and 1. That is, when in classical bit, we can either have a 0 or 1, we can have a state like this one, alpha 0 plus beta 1. This is like this one, linear combination, it is possible. Thus, what is important here, there is a probabilistic interpretation of this one. If we want to measure something on it, then it is alpha beta, not A and B, not that, it is A and B. So mod A square plus mod B square is equal to 1. You can see that there is I should say some shadow of probability in it, as because quantum mechanics is essentially a probabilistic subject, probability being engraved in the basic geometry and structure of the Hilbert space, the quantum mechanics uses. For our purpose, the Hilbert space is linear space because in quantum information theory, we will use just finite dimensional things. And this is actually used here, which is not the case with the with other parts of the areas of applications of quantum mechanics. Here, just finite dimension is sufficient. So psi 0, psi is A0 plus B1. It gives, when we measure it, then it gives 0 with A square probability and 1 with B square probability, and mod A square plus B square is equal to 1. So essentially what is done here, if you want to see it mathematically, the bits from bits we have the 0, 1, that is the Boolean algebra structure. Whereas in the qubits we form a vector space. And as because it's a vector space, the linear combinations are allowed. This is the basic mathematical difference, but in applications it makes a lot of difference. We will come to that. Now, any communication system can be just, we can look into at the diagram and see what a communication system is. Firstly, the task is of encoding. We encode something. That means in symbolic language we write, and then we there is some communication channel. If you have a mobile in your hand, then mobile communication is that through a satellite, something encoded is going to the satellite by electromagnetic means, then get processed and reflected from there and reaches your frame. And in the mobile of your frame, there is a decoding mechanism. It will just decode and give you the message in the way you want it to be delivered. If you are talking to your friend, then your friend will want that you listen the voice. Then he or she can listen. Essentially, there are three parts: encoding, communicating, and then decoding. Here you will see that in the process of encoding, sometimes if you have a message, then a typical way of encoding is to use 000111, 0110, that is the sequences of zeros and ones is the way of encoding. But here, there is something very special with the quantum mechanics. Now you look at this one. So in the process of encoding, what happens that one may have the idea, yes, we are using the symbol 0, 1 for encoding, right? We will use 0 Kate and 1 Kate for encoding, like this one. But you will be faced with a difficulty. In the whole process, your replication is not allowed. This is the no cloning theorem of quantum mechanics. This is a restriction as well as I should say, a virtue of the system. It will restrict you from doing many things, and it will restrict your hacker from getting into your system in many ways. That is, you cannot have a machine like this one. You give your psi, then you have a psi. It's not possible to have replication of the quantum state. It's a fundamental result. And when you look at it, let me go back to its implications a bit, I should say, a bit outside our discussion. There was a particular, I should say, this is a protocol which was advanced in 1970s. That was faster than light signaling, that which is called flash by name. That in through quantum means we can make a faster than light signaling. So this was in contravention with the theory of relativity. As I told you, that this is an integral part of our understanding of nature, and this does not allow this one. So there was a conflict between the two, and the conflict was resolved by proving this no cloning theorem. What is no cloning theorem? In that particular faster than light signaling process, that is flash, they used that in certain intermediate step, they used that one quantum state is cloned, that is the replica of that state is made. And this is prohibited by quantum no cloning theorem. There is another implication of the theorem. You will see that in biology, cloning is something which is much talked of nowadays. Now, the point is that although in very recent times people have the enthusiasm over cloning has come down to some extent. Now, if you look into the basic structure and of matter, even of the biological stuff, the DNA and RNA go far inside into it, then you will see that you are confronted with particles which are quantum particles by nature. That is, they obey quantum laws. And if you go into RNA, you find molecules, and then you find atoms, you find the subatomic particles, then you find quarks, and etc., etc. There the no cloning theorem is applicable. Now you think that quantum mechanical particles, they are the building blocks of nature. It is like bricks of a mansion. If no two bricks are equal or can be made to be equal, then is it possible to have identical two mansions? So when you apply quantum mechanics to biology and try to explain life process, not really life, because life cannot possibly be explained in that way, but life process, if you look from a quantum mechanical angle into the life process, then cloning is an impossibility. This is again a new direction which has emerged, which is called quantum biology. There is a complete negation of biological cloning. Anyway, our business is not that. So this is with quantum cloning, and you will be surprised with the simplicity of the proof. It is like that we are putting the state in a machine, and this machine is like just a Xerox machine. You just have a Xerox copy of your paper and then take the paper out. Yes, you put a machine here, then psi becomes here, but you have a linearity requirement. This is a very simple mathematics. You can see even first year undergraduate students can follow this mathematics, and then you have a perfect contradiction. I say it's a perfect contradiction. Why a perfect contradiction? Even by imposing any condition whatsoever, you cannot avoid getting contradicted. It's something which is built within the structure of the quantum system. So it's not possible. And again, you will see, this is an, incidentally, this was the no cloning theorem. It was in 1982. This was the work of Reuters and Zurek, two famous physicists. Now, what I come to is an Indian contribution, incidentally. This is just the reverse no deleting theorem. If by any chance in nature two identical things are there, then you cannot simply delete out one of them. Impossible. This is the no deleting theorem, and this is the complementary part of the no cloning. So in some day, if some quantum computer is in use, sometimes what you do is that you copy one file and then there are two copies of the single document. You just delete one document. It will neither be possible to just copy the file exactly. This is, I say, exactly. What I'm trying to tell, I will tell you later why exactly I am using the word. And if you have by chance through the system two copies, it is possible because through fabrication in some other way, the explanation is otherwise. Anyway, if you are given with, let us start that we are given with two copies, you cannot perfectly delete one copy. Why I say perfectly? It is possible to do approximately and probabilistically. There are both deleting and cloning approximate machines and probabilistic machines. Anyway, this is not our job. Our job is to show, is to learn, is that what is the, I go back to this one. So when you are going to encode something, you make multiple copies, normally in the case of your classical encoding. This is not possible in quantum encoding. Simply like that, you make copies and delete certain copies in the process of decoding. This is not possible. So these two things are quite different in quantum communication systems. And the technology to implement these ideas are bound to be different. But we are mainly, this is to give you an idea of that, but we will mainly concentrate on this part, particularly on this part, not going into the details of this part. They have their own problems, their own modalities, and etc. Some quantum encoding and decoding have been done very successfully. And anyway, we are going to the communicating part. That is on which we will concentrate. Now, in this part, there is something which is called entanglement. What is entanglement? If we go back in history, then it was a paper of Einstein, the EPR paper of 1935. Incidentally, this paper was against the quantum mechanical formalism. Einstein and his collaborators, Podolsky and Rosen, had argued that the quantum mechanical argument cannot be complete. Why it cannot be complete? Because this involves certain formulation, which we know today as entanglement, which will give you counterintuitive results, which was not acceptable to Einstein. And it was followed by very elaborate discussions and etc. The discussion was mainly on theoretical and philosophical level until in 1964, Bell could give an inequality, a testable inequality. You can test it in experiment and see really whether the idea of entanglement is tenable or not. If it is not, then quantum mechanics is bound to crash. We are bound to recognize that if it is not tenable, then really we will have to look back and look into the some alternative theories of quantum mechanics, and it was already, the seeds were already there. The Bohmian mechanics was in development, but it was discouraged later on. And the experiment, the conducting of the experiment was not very easy. He gave some inequality which can be tested for yes or no by some designed experiment, but that particular designed experiment was not very easy to perform. But eventually these were performed. Even after performance, the results of these experiments were not beyond doubt. Still, by another 20, 25 years or 30 years, I should say, now we are in a position to recognize that the impossibility of quantum mechanics, which was targeted by Einstein for establishing through the idea of entanglement, is a possibility. And we can today create entanglement. And this is the heart of quantum communication. What is entanglement? Entanglement is something which I can say, suppose two particles are created. Suppose just we break one particle into two particles. There are many ways of doing that, electron positron creation and etc. etc. Many ways of doing. Every day the particle physicists are doing that, experimental particle physicists I mean. And then these two particles get separated in the opposite directions, miles away. Hello, am I audible?
Yes, sir. Yes, sir.
Yes, my system is giving a signal that your connection is getting disrupted. Anyway, if I am audible, then it's okay. Then they are going miles away, even light years away. There is no visible connectivity between them. Still, there is a connection. That is the quantum mechanical connection, and this is called entanglement. Light years away are there. There on your right there, it has gone through 100 light years, and on your left, it has gone 200 light years. So the distance is 300 light years, and still they are having connections between them. What type of connection? They are connected not by mechanical threads, they are connected. Even they are not connected by your electromagnetic means, because the light can only travel in the speed of, with the speed of 3 to 10 to the power 10 centimeter per second, which is the highest possible and highest conceivable speed in fact. So it's not electromagnetic. Then what type of thing it is? It is here lies the heart of quantum mechanics. It is the quantum mechanical, purely quantum mechanical connection. Now our endeavor is that, can we harness this entanglement? Can we use it in performing some job of communication? Definitely this communication job will be very, very different from the communication which we make by electromagnetic means, and possibly much more richer in its content. And what is impossible to even to think by electromagnetic means can be possible with the help of quantum communications. This possibility is there. But as because you will see that it is only, as I told you, the primary possibility was only explored in this paper, which is in the year 1993. Teleporting and unknown quantum state via dual classical and EPR channels. So the protocol is called teleporting, or now today is known as teleportation. What the teleportation is, let us go on. Now, before that, we will have something to say about entanglement. Yes, what is entanglement? Two subsystems A and B. As I said, the system A, very simple system, just an electron having spin up and down. Can be described by two-dimensional Hilbert space, or we need not use the terminology of Hilbert space, two-dimensional linear space. And B is another state of a system, another particle, which is also given by two-dimensional linear space. Then the combined system is like this one. Psi A is equal to first system, then product, and this is actually the mathematical way of writing the tensor product, we call it, and then psi 2b. This is also part of elementary linear algebra. And then they are, when this cannot be written in this way, then we call it is entanglement. Now it can be written in this way because if it can be written in this way, this one goes to the left and this one goes to the right. No one bothers if you make certain operations on B, there is no effect on A, and you make certain operations on A, there is no effect on B, but this will not be the case if you have this type of thing. Simply think, there are two particles, two systems, to be more formal. Then one is given by this one, the whole system is given by this one. It is impossible to write them as product of two individual systems. They have been entangled in some way, inseparable. And you cannot make them separate in an ordinary way. And so one goes to the left for 100 light years and the another goes to the right with 2000 light years. Nothing happens with their relation. The relation gets persists. And when you make a measurement or some disturbance on A, even 3000 light years they have been separated. On B, it will be felt. And this will be felt instantaneously. So there is these states are called Bell states, very famous Bell states. So if these are the types of things which are quantum mechanically related, and we can just strike on one part of the system and the effect is felt on the other part instantaneously, very far away, without any connection. Only there is a quantum mechanical means which is not electromagnetic and which is not a mechanical thread, so that we do not have just an explanation of that in terms of our classical physics, but do have explanation in terms of what we have the new physics of quantum mechanics. And then if we can use it, whether use is possible, the answer was yes. Using this is possible, but there are ifs and buts in it. So this is the convenient way of writing. We just, unlike in the previous slide, what we do here is that we just put them in the same bracket, write AB this way. And as I told you, there are several other types of things. As you can see, I am giving the, even with the three, if there are three particles, they can also be entangled like that. The three particles created in some position and then going in three different directions, still maintaining some quantum mechanical correlation, which is entanglement. If there is an N particle, this is called the Geilinger and etc. This state, they have discovered and studied it. So the GHZ state is like this. And so we can have N particle entanglement, not only two particles. And so the the scope of communication, as you can directly see that you can hope to make some arrangements so that this can be explored and exploited. Yes, we can. This is actually called the quantum teleportation protocol. I will dwell upon it briefly to give you an idea, because I have the caption is Introductory Quantum Communication Theory. So I will introduce you to what teleportation is. And you will readily recognize its limitations. If you think that in this way we can just evade the maximum velocity of light and put our information which is faster than light, no, it is not possible. Because it has to be supported with classical means. Otherwise, it is not possible, not yet possible. Suppose there are, traditionally we call the two parties, Alice and Bob. These have become very generic names, Alice and Bob. They are sharing an EPR state. That is, Alice is having a state which she wants to just teleport or just transfer to Bob. And Alice and Bob are connected with the Bell state that I showed you. That is the EPR pair. And there is a conventional channel like some telephone operation or a mobile operation by which they can also have communications. But this mobile operation or telephonic operation is unable to transfer this quantum state from one place to another. This is just a thing that quantum states definitely and generically have in them quantum information, which is very different from the classical information, and classical channel can only carry classical information, not the quantum information. This is a result. The proof is otherwise and will not be, I cannot include it here because
Hello? Sorry for the inconvenience. Vinayak sir has disconnected somehow.
Continue, sir.
hello.
Yes, sir. Shankar, sir. Vinayak, sir, please continue, sir. I think there was some internet issue. Yes, sir.
Okay. Okay, sir. Please, sir, continue, sir.
How much time? Hello.
Okay, sir.
I can continue.
Yes, sir. Yes.
Yes.
Okay. So what I was there. Was I audible at that point? Then the requirement of quantum teleportation. I was audible on this slide.
Yes, sir.
Yes. Okay, so the qubit is to be reported and is an entangled Bell state. That is the quantum channel, and the conventional channel is there. Why we use conventional channel is that we want to teleport the quantum information, and conventional channels like telephonic channels or mobile or electromagnetic channels, they are incapable of just transforming. Then this is the qubit which Bob wishes to transmit. This is the qubit. Okay. Then there is a channel between the Alice and Bob. This channel is given by this one. So Alice has additional 1 qubit at hand. So the combined system is now this one. As you can see that this is with tensor product, this one. And if you just write in this way, you will see that this comes out. This is the rearrangement of writing. Then with this, Alice will make a Bell state measurement. What is Bell state measurement? It is a quantum measurement by virtue of which, if Alice wants to measure the bits A and C in her hand, then the 0 bit will be just, left out. And then if the measurement comes out to be 0, 1 with AC, then again 0 bit. And 1, 0, this AC, then the 1 bit is there. Now measurement is this is a very important concept of quantum mechanics. When you measure, you irretrievably disturb the whole thing. That is, what you mean irretrievably disturb? Because after the measurement, there are no ways and means of getting back the original one. The original one will be destroyed. And here also, after the measurement, this Bell state is destroyed, which I am trying to tell. This entanglement, and I will dwell upon that, it is not very easy to create entanglement. Although now we know that entanglements do really exist and we can create it, but it's a very costly creation. How you can do that? That is cavity quantum electrodynamics, then nuclear magnetic resonance technique, that is the NMR technique. All these techniques can be used to create quantum entanglement, and it's not a very easy task and involves a lot of cost. We in our country cannot make, in most places, cannot make the experiment with the entanglement. Why? Because even a simple device for creating and doing experiment of with entanglement will cost you 150 crore. So this is a very costly thing. And once you perform the experiment, teleportation, in the midway, the created entanglement is totally destroyed and it cannot be retrieved back. So it's one-time use. But it's a technology demonstration. And because I am telling you that this is a futuristic technology. Why futuristic technology? Today, if you say that we cannot, are we using teleportation? No. Answer is no. Why? Because firstly, not only that due to cost, again it is that the entanglement will not sustain in ordinary environment. Only in very special cryogenic environment or in other very special environment we can just create and preserve entanglement for use. But once you make measurement, which is a part of the protocol, the entanglement is lost. You are left in your hand with just these four, the final four states. Now, by protocol, Bob knows, because when the protocol starts, Bob has been educated with certain instructions. Bob knows that if he is having this state in his hand, what to do? He will apply the operations. These are the unitary operations he will apply. And after applying the operation, he will get back the state which was intended to be sent. And as you can see, if you are associated in some way with quantum mechanics, then you will see that the unitary operations here are given by the Pauli spin matrices. So mathematics is quite simple. And just at this stage, what is the role of applied mathematics is that if you are doing mathematics and then you are actually exploring the possibilities and frontiers of the future, this futuristic technology. Not really that you are getting yourself bothered with how to make a machine or like that, because if you give the possibilities that yes, this can be done this way or that can be done that way, and then putting these atoms here, those wires there, putting these this much of quantum electrodynamic, that is some operators and corresponding the devices there. This is not your job, not the job of mathematician. I mean, not it's an engineer's and scientist's job. From the mathematical point of view, when Bob applies these operations, then the original state which was intended to be there is in the hand of Bob. This was the original state. Now it is lost from Alice and it goes into the hand of Bob. One thing is very important here. If you say that whether Alice has any knowledge of this state in her hand, this is not necessary for Alice. Because Alice is, suppose on the one part of communication system, Alice is sitting and Bob is sitting on the other end, then I take some quantum information encoded in this particular qubit, give it to Alice, don't open it, just put it in your machine and transmit it to Bob. That can be done with Alice, by Alice. And because of that, there is no need for Alice to know what actually the state is. But if Alice knows what the state is there any gain in the protocol? Yes, there is a gain. And for that part, we have remote state preparation. That means the state is known to Alice. Alice wants to transmit it, to prepare it at a very distant end. Again, let me repeat, it may be on the surface of another planet or on the surface of another star, on the even. And this is the reason why these types of protocols are so much important in problems, emerging problems of space science. And also why these problems are so much important in military applications as well. You will see that trillions of dollars are being diverted to the development of these types of protocols by the US military system. And if you go into the, I think, February or March, that is, I cannot give you the reference, but you just consult the Nature magazine. That is in February or January or February or maybe like that, or March. You will see that there is a report that India government is also giving priority to it. The Nature reports that it is also giving or investing or diverting fund to the research of these types of protocols, and the fund is single largest in any amongst any individual category of funds. So anyway, this is a hot topic. Now I will go into the what type of researches are there, and you can see that again in Nature, it was in 1993 the protocol was proposed. By 1997, Zeilinger and etc., they could make experimental quantum teleportation possible, but in a very, very controlled atmosphere, in a cryogenic atmosphere where controlled teleportation was done in, I believe, in minus 240 degrees centigrade atmosphere. But in 2017, there is a, this was very widely publicized and Nature published it. There is a report of ground to satellite quantum teleportation. This is by a Chinese group. From satellite to a ground station, the quantum teleportation was made possible. And this is a quantum jump in not only in technology demonstration, but also in the military technology, which China has developed in very recent years. And in this paper, if you read this paper, there are certain portions which are not disclosed. Only the final result has been disclosed in this paper. But just going through this paper, this is not, it is a quasi-scientific paper. This is a report kind of thing. And the know-how is classified. It is not made public. Anyway, this is a glimpse of this protocol, the elementary protocol. Then we have many other types of protocols, then noisy channel protocol of teleportation. This is also something, as you can see, in every communication system, noise is something which must be which should be present in any practical situation. And in quantum system, that is, when the quantum system, as you can see, the channels are quantum systems. When the quantum system will react with the environment, this becomes a becomes an open quantum system. And there are developments of that. Then joint remote state preparation. If you want that quantum communication will not be accessible by a single party, if you want to just divest it among several parties, they can join hand and to make teleportation possible by DRSP ways and means. This is I should say that I should come to an end of what I intended to tell you by telling you that this is a glimpse of the quantum communication possibilities. Let me again repeat one thing, that the as I firstly asked that whether the audience is mostly from mathematics background. In mathematics background, we are in a position to explore the possibilities which can be done, what this quantum science allows to be done. And this is important because the technology will follow these possibilities. It will chase these possibilities. And you see that quantum computers are something which is very much associated with quantum information, and also to a very large extent with quantum communication systems as well. As because you can see that through computers, even we are communicating through computers. So one thing is important to recognize, that not really tomorrow we are going to make a quantum computing system or communicating system and put it to use. it will be for public use, it will be another 100 or 200 years. That is the forecast of different universities like Oxford University or that type of university which are having strong centers for quantum information and computation. Their planning is like that, and the role of mathematics is to pave the way. If you want to have a something very comprehensive and very introductory as well as comprehensive, yeah, I will refer you to this particular book, that is Quantum Computation and Quantum Information. If someone of you have the idea, I don't assume that everyone is having that idea, because the mathematics people only, it's a specialization of applied mathematics. This book will be of great value, and it is Cambridge University Press, but it has Indian edition. Lots of Indian editions have been sold, and its cost is quite low. There are also other books. These are good books. Quantum Information Theory in Wild. This is an involved book by mathematicians. So. I think should go up. I thought that I had some more references for you. Anyway, let me come, because I think it's 1 hour. And if you have any questions to ask, I am free here to answer. What will fall within the purview of my knowledge.
Thank you very much, sir, for this nice presentation in introducing quantum communication theory in a so simple manner. The role of quantum technology and communication is very nicely explained by you in the domain of communication science, starting from its historical development. Thank you, sir, again for your wonderful presentations. Sir, now we shall take some questions from the participants.
Yes.
Okay, sir. The first question is, how do quantum information theory and quantum computing related?
We can take the analogy of how the classical information and classical theory of computation is related. Just like that. In a computer, if you open the computer, then there are certain units which together make the computations possible. And there are also certain units, and they will also play the same game. Just like that, there are gates. So here we will get quantum gates. What are quantum gates? Those perform the ordinary operations of gates, but in a quantum way, and that too not on bits but on qubits, just like flip play. 1 to 0 and 0 to 1. It will flip just to 0 gate to 1 gate and 1 gate to 0 gate. But be sure that there are certain superpositions of 0 and 1, which is not in the classical bit. And so these gates have to be amended or quantum mechanically decided accordingly. And their fabrication is also a very challenging task, because working with quantum gates, we have only become successful in starting with 2014, 15 or like that, 5 to 6 years back only. So basic principles of quantum information has to be spelled out in terms of, in machine terms, if you want to bring out a quantum computer very successfully. But once you get it done, then your polynomial speed will be converted into exponential speed. But there is another negative virtue for that this is a probabilistic theory. There will be always a chance of failure. and it will be probabilistic. If you fail, then your resources will be totally destroyed, but by chance, there is a probability of getting failed or getting success. If you succeed, then you will have success, an exponential rate of success. But you don't know really, you will have to depend on probability, and there is one optimization type of thing that you can optimize your probability of success. This much you can do, but cannot totally eradicate the case of failure.
Thank you, sir. The next question is how quantum information theory is applied in traditional computer networks.
Additional computer networks, there is very little scope of applying quantum information theory except for certain simulations. That can only be done. Because you see that quantum probability is also characteristically very different from the Bayesian probability we use. Its foundation, is not Kolmogorovian. It's very different. And so what we can deal with the classical machines is not applicable to quantum machines.
Thank you, sir. The next question is group geometry, topology, and quantum computation, how they are related.
Yes, they are related in a very large way. I have not touched upon that particular aspects, but if you want to learn these aspects, then I can say that there are good books, actually, very recently published good books. I have not the references out there, but these books give a very vivid idea of the connection between these things. And actually, you see that when you do very seriously quantum mechanics, then group theory plays a very great role. And in quantum field theory, you will see that the role is actually very much played by your topology. And even in continuous groups, that is Lie group type of structures, which is actually of importance, there are also topology, algebraic topology, etc. These are of very great value. In fact, without that, the subject cannot be successfully pursued. And here also, if you want to have a very rigorous treatment of the flow of quantum computation or like that, you will have to go to geometry and topology. And it is actually a developing area. I don't say that just like the classical ones, the group theory has developed and supported just like it supports the particle physics or those types of things. Here, this is a developing thing. If you open the journals like Physical Review A, there you will find the quantum computation and quantum information theory as a section. And there you will be seeing that there are many proposals using topologies and groups, and it is actually the developing and the subject is in the making.
Thank you, sir. The next question is, what is the advantage of using quantum communication theory over classical communication theory in context of security of IoT devices?
Security of?
IoT, Internet of Things.
I see. See, that quantum computation has not, quantum communication has not advanced to that extent to give you an internet network. But if you look into the safety aspects of quantum communication, not only of quantum communication, but also quantum key distribution, quantum cryptography, that is the famous BB84 protocol was there, Bennett-Brassard 84 protocol. Incidentally, it was first publicly announced in Bangalore in 1984, as back as early as in 1984, when teleportation was not, idea of teleportation was not there. After that, regarding noise and security, this has been a great aspect of quantum computation and quantum communication theory. And regarding that, we see that if in some days we spell it out in our machines, then definitely the aspect of quantum security will be much more better than the classical security. The hacking and etc. can be largely avoided by using quantum gates.
Right, sir.
And this is actually told you that there are, I have shown you the two theorems, that is no cloning and no deletion.
Right,
So
right, sir.
simply, so you can have an idea, an intuitive idea that hacking and etc. type of things will not be that easy with the quantum devices. And it is like that. You can have a mathematical proof of that even. That in order to get hacked, you will have to make certain operations which will not be permissible in the quantum domain.
So next question is, how can communication, quantum communication can be used in astrophysics, like extracting signals from extracting signals in observational astrophysics or observational cosmology?
Yes, it's a good question. It's a good question. I had not much idea of that beforehand, but very recently I was going through certain literatures. Now the point is that we are creating entanglement in our, trying to create rather entanglement in our laboratories and etc. But entanglement may be a very natural phenomenon. It can be automatically created in stars, far distant stars and distant galaxies. And that photon or that particle which we are just catching in our telescopes or like that may have some entanglement in the past with some other particles in distant galaxies and etc. And there are very interesting ways of analysis of that by which we can extract information. Even quantum information may be very important in having information on black holes. This is something I should say that this is promising, and if it is successful, some information can really be extracted in a very unambiguous manner, then it will give a separate flavor to the study of entanglement, definitely. But definitely, the one thing is very important, that regarding entanglement, our idea is going to change, because now we recognize that entanglement is a natural phenomenon, not something which we create in our laboratories or try to create it in our laboratories. It's a natural phenomenon, and through astrophysical observations or like that, we can possibly reach an unambiguous conclusion on that.
Thank you very much, sir. Thanks again for your nice presentation and being a part of our faculty development program, and giving us opportunity to hear from you as a so nice presentation. Thanks again, sir. So this is we are near the end of our session now. I shall request our participants kindly to.
I have one thing to tell. I have
Yes,
one
sir.
thing to tell. You can possibly, I'm sharing, you can possibly see my email, and also you can go to my website. You can also find email. If anyone is seriously interested in the study of quantum communication theory, and this lecture is only an introductory one, can give you some, cannot satisfy you, because this is very brief, and within 1 hour it is not possible to introduce this subject in a very, I should say, in a very successful way. So anyone who is seriously interested in this study can get contacted. I'll be happy to answer any serious question if it is sent to me over this mail.
Okay, sir. We have noted down your mail, and of course, we shall send this email to our participant and we will share it. And thank you, sir, for all your references you have given. These are really, really very useful for all of us. and basically the participants who are interested in this field. Um, I hope the participants have been benefited a lot from this lecture, and will go back with some stimulating thoughts with which they can work on this field in future. Thank you very much, sir. So this is so we are near the end of session. So I'll request our participants kindly to fill up the feedback form, and we are about to end this session. We'll meet again tomorrow at 4 p.m. and with some nice presentations again. We have 3 lectures tomorrow. The abstracts will be sent in due time. And I thank all the participants for considering us and for participating in such a enthusiastic manner. Thank you so much. So I end the session here. Thank you. Good night.
Okay.
And thank you, sir.
Okay.
Again.
Thank you very much. Thank you all.